Hello, all the future doctors and the IITians watching this session. Welcome to the Unacademy NEET English YouTube channel. I'm Kailash Sharma and today I'm going to teach you kinetic theory of the gases and thermodynamics. This is a very important topic for NEET as well as for the JEE main. So students who are preparing for the NEET 2024 must be benefited by this session if they completely watch it. Because I am going to completely cover the two topics. One is kinetic theory of gases, we call it KTG, and the other is thermodynamics. So both the topics will be covered in the next 3 to 4 hours, and this is going to be an amazing session because each and every concept, as I tell in each and every class, that we will cover in detail. We will solve the numericals on that, and we cover that topic for the best way for our exam. So I'll start the session. Before that, I want all of you to like this session, share and subscribe this YouTube channel where you are getting the amazing content for your NEET 2024. So so are you excited for the session? I asked yesterday also on the Telegram channel and I got a very positive response from all of you. So that response again I want to see in the chat box. So are you excited? Because this is the first topic which is a purely physics topic and very important, or you can say directly questions are asked from this topic, and this is an easy topic as well. You'll say, sir, who says thermodynamics is easy? I say because in physics the thermodynamics is not that difficult as you study in the chemistry. So as compared to chemistry, in physics thermodynamics will look more easy to you. So because I teach the way, I'll teach that way that you find it very easy. So I am about to start the class. I am just waiting for all of you to join the session. I can see the excitement among you in the chat box. So let's start the class, students. So this session is going to be 3 to 4 hours long, and before I start the class, I must tell you that there I have planned a special class as well. I'll cover theory and we will solve 12 to 13 questions in this session. Apart from these questions, you need to practice more questions on this topic, and that you can do in the special class. The special class is will be conducted tomorrow at 2 p.m. where we will be solving numericals based on the theory I have covered in today's class. So you have to watch this class till the end. You have to make notes and then attend the tomorrow 2 p.m. special class, and after that this topic will be completed for NEET 2024, or the students preparing for the JEE Main 2024 can also be benefited by watching these two classes. So basically it is not a single class on this topic. Special class will help you understanding this theory part in detail. So you have to watch that class as well. So where do you find the link of that special class? In the description. In the description there is a link of the special class which will be conducted tomorrow. So we will solve numerical in that class. Today we are going to cover the theory, and to support that theory, to understand that theory, I'll be solving, or we will be solving some illustrations along with the theory part. And there is one more link in the description and the chat box, and this link is very useful for you. We at Unacademy, the top educators of NEET on Unacademy, are going to start a crash course from 2nd of January, and that crash course link is pinned in the chat box. You must go through that crash course. Just go through that crash course. See, your all favorite educators are there in that crash course for NEET 2024. Go and you can subscribe for this crash course. You can buy this crash course, and there is a referral code which is Kailash10. Use that referral code and subscribe or enroll for the this amazing crash course. So let's start the class. I hope you all have all the students, or the regular students have already joined the class. So now I can start the class. Somebody is saying NEET English channel पे NEET हिंदी का ad आ रहा है. This should not happen actually, ना? Correct? This should not happen. So anyways, so I'm going to start the class. Did you like the session? Can I see the likes on this session have already crossed? Yes, the likes on the session have already crossed 100 likes. And guys, keep one thing in mind. After this session, you are supposed to share your feedback in the comment box. Please do share whatever you feel after watching this session. If it was amazing, it was not that helpful, whatever you feel, just write after the class ends, and you have to write in the comments. Please share your feedback about this class, about your experience with this class. Don't forget to share that. It is not about the feedback, it is about the you can motivate me like I motivate you by covering the topics in very detailed way. So the same way that these things ultimately push us to work more, but work harder for all of you. So please do comment after the session. This will definitely help us in understanding the problem. If you are facing any problem, that if it can be eliminated from our side, we will definitely do. So don't forget to share that. So let's start the KTG and thermodynamics topic. Now we are going to talk about the topic only. Okay, so are you ready for the session? So we start the KTG and thermodynamics. So I'll start with the KTG, obviously, kinetic theory of gas. So what are the topics I'm going to cover? There is a list of those topics. Always in the beginning of the class, I give the overview of the topic. So first we will talk about the postulates of the gas. We will understand the gas. What is KTG basically? KTG is the kinetic theory of gas. There is a theory given to understand the ideal gas. So there are certain assumptions taken to understand a gas and to consider a gas as an ideal gas. So those postulates we will study in the beginning, and then we will go to VRMS, derivation of VRMS. We understand the VRMS and the pressure of the gas. What is the pressure of the gas? So we are going to talk a lot about gas. We are going to understand the gas. We are going to talk about the conditions which makes a gas an ideal gas. And what is RMS? What is the pressure of the gas? Those are the parameter of the gas. Internal energy of the gas, a very important term, that is the internal energy of the gas. You know, in chemistry, you are like, when I used to study for my IIT JEE, when I was doing IIT JEE preparation, there was a word in thermodynamics in chemistry, enthalpy. That was like very difficult to understand that thing. But here, there is no such word. In physics, there is only one word we will be using, that is the internal energy. What is the energy of the gas? Internal energy we will talk about. We have already understood the pressure of the gas, internal energy. First law of the thermodynamics, then we will enter into thermodynamics, where there we will talk about first law of the thermodynamics. Then we will understand work done by the gas, not on the gas. We will talk about work done by the gas. We will study this thing, work done by the gas. Different processes on the gas, cyclic process and the Carnot engine, Carnot cycle. Heat engine and the heat pump we will talk about. This part is not in the syllabus, but this is a very small portion of 15 to 20 minutes that we will cover. There are the 2-3 formulas. If any chance they ask question from this, so you should be able to solve that. Second law of thermodynamics, mean free path, which is the part of the kinetic theory of gases, that we will cover in the end of this topic. So this is the order of the topics to be covered in the today's class. So let's start with the first topic, and that is the postulates of the KTG, kinetic theory of gas, postulates of the ideal gas. So before I start, I must tell you one thing. Today, two topics we will cover. One is the kinetic theory of gas. So in kinetic theory of gas, we are going to understand a gas. When a gas can be treated like an ideal gas, that we will understand. What are the certain conditions which makes a gas an ideal gas? Because in physics, we are only talking about ideal gas. There is very rare question from the real gas, very rare question, or very easy question is asked from that part. Otherwise, it is not asked. So we only talk about ideal gas. That's why I told you that thermodynamics in physics is very easy to understand, because we are only talking about the ideal gas. So when we are talking about the ideal gas, we will understand the gas parameters. What is the pressure of the gas? What is the VRMS of the gas? What is the relation between VRMS, temperature, pressure? All these relations we will derive. And then we talk about the internal energy of the gas. We will understand what are the things on which internal energy of the gas depends. Yeah, what is the energy of the gas? These all things we will cover in the kinetic theory of gases. Okay, is this clear? Like, why we study kinetic theory of gas? To understand a gas, to understand its energy. So energy of the gas we understand. About the gas we understand in kinetic theory of gases. Is this clear to all of you? Kinetic theory of gases are all about gas. We are understanding a gas, ideal gas, its energy, its pressure. Then we move to thermodynamics, where we talk about so many different processes. They are isothermal, isobaric, isocoric, adiabatic. Those processes we talk about in those processes are done on the gas. But we need to understand gas, so we first cover KTG and then we move to thermodynamics, and there we study different processes done on the gas. In those processes, what is the change in the energy of the gas, internal energy of the gas? What is the work done by the gas? How much amount of heat supplied to the gas in a process? That we will be able to do if we understand the gas, if we understand the internal energy of the gas, if we understand the work done by the gas. Then and only then we will be able to relate the change in internal energy in any process, heat supplied to the gas, work done by the gas. These all things can be understood if we understand the gas. That's why there is this topic. I hope you all understand the importance of this topic, why we study the KTG, because for the last 5 to 7 minutes I'm just trying to make you understand why this topic is important. And this topic is 25% of the total content we are going to cover today. But the questions asked from this topic are 75%. So 75, if you say 4 questions are asked from the KTG and thermodynamics, suppose let's take an example. So 3 questions will be from the KTG only. There will be very rare chances that 2 and 2 questions are asked from the 2 portion, but the KTG has more weightage as compared to thermodynamics part. But the thermodynamics part is more lengthy as compared to KTG. So KTG is very important. Okay, so let's start kinetic theory of gas. So we are talking about gas a lot. We have already talked about gas. So what is gas? So it is a collection of large number of molecules in random motion. Collection of large number of molecules in random motion is called the gas. The molecules in random motion and a large number of collection of large number of molecules is called the gas. So this is the basic definition. I hope you all are aware of this definition. So gas we have already defined. Now see, you have to make notes. You can I'll be covering the topic in like slowly we will be going ahead. So in that meantime you can note down all these things. So definition of gas is clear to all of you. It is not something very very special about it. Okay. So now we are going to talk about the postulates of the gas in the steady state. I told you we are going to talk about ideal gas. So there are certain assumptions we have taken, certain conditions, certain things we have assumed that a gas can be treated like an ideal gas if this gas satisfies these particular conditions. And those conditions or those assumptions, postulate, the other meaning of the postulate is assumptions. So we have taken some assumptions for a gas to be treated like an ideal gas. What are those assumptions? What are the those conditions which makes us understand, which will let us understand the gas? Those we are going to cover here. So there is first condition, that is the first postulate is a gas consists of the large number of small, smooth, spherical elastic and identical particles known as molecules of the gas. So this is the first condition. This is the more this is the definition of the gas only. Okay, this is the definition of the gas only. So a gas consists of a large number of small. So these molecules are very small as compared to the container in which they are kept. They are smooth. There is no friction force involved. When there is a certain kind of collision of the molecule with the wall and between the two molecules, they are spherical. We are treating molecules as spherical. They are elastic. So no loss of energy during the collision is there. So what we are treating is, we are treating here a gas molecule as a small, smooth, spherical and elastic identical particle, and they are called the molecules of the gas. So basically, this first postulate is mainly talking about the monoatomic gas, because monoatomic gas has spherical molecules. Monoatomic gas will have a spherical molecule. Diatomic has a dumbbell shape. Triatomic and polyatomic might have linear or non-linear shape. So basically, we are going to first talk about the monoatomic gas, but they did not mention that we are talking about only spherical monoatomic gas. But this definition indicates that we are talking about the monoatomic gas only. A gas consists of the large number of the small, smooth, spherical, elastic and the identical particles known as the molecules of the gas. Later we will generalize our discussion to the diatomic and the polyatomic molecules. Here, volume of the container, this condition of the small can be can hold only if volume of the container is much greater than the total volume of the molecules. So if you take all the molecules and keep them together, and then the total volume of all the molecule must be very small as compared to the volume of the container in which these gas molecules are kept, then this gas can be treated, this condition can be satisfied, and they are smooth, spherical and elastic that we are already considering. So this is the first postulate of the ideal gas in the steady state. This is the first postulate. This is the first postulate. A gas consists of the large number of small, smooth, spherical, elastic and identical particles known as the molecules of the gas. I hope we have already spent a lot of time on this slide. You all might have already written it. Let's move to the next slide. So there are other postulates as well. The molecules of the gas move randomly in all the directions without giving preference to any particular directions. So when molecules of the gas inside a container does not give any preference to any particular direction, like they all will not be moving towards the right, or they all will not be moving towards the left or upward or downward. They all will be moving randomly without giving any preference to any particular direction. The molecule of the gas move randomly in all the direction. They move randomly in all the direction without giving any preference to any particular direction. When I read a statement, you have to note it down at that time. The next postulate says the distribution of the molecules and that of the velocity will be same at every point of the container. So the velocity of the center of mass of the gas is equal to 0 with respect to container. So let's say there is a container. We take a small volume here and we take a small volume here. These two volumes are identical. So the number of molecules in this volume will be equal to number of molecules in this volume. So we take anywhere the same volume, we will find the number of molecules are same in all the volume. We are considering that distribution of the molecules is uniform. You take any dV volume in any part of this container, the number of molecules will remain almost same. The way these molecules will be moving, the velocity distribution will also be uniform. the molecules in this volume will be moving in a particular way. The same way the molecules in this volume will be moving. The same way the molecules in this volume will be moving. So the distribution of the molecules and that of the velocity will be same at every point of the container. And the velocity of the center of mass of the gas is equal to 0 with respect to container. So when a container is at rest, the center of mass of the gas molecules will remain at rest. When the container is in motion, the center of mass of the gas molecules will also be in motion. Is this clear to all of you? So all these two there are total 3 postulates we have covered till now. Fourth postulate is there. The molecules exert no force on each other and walls of the container except during the collision. The molecules exert no force on each other and the walls of the container except during collision. So there is no interaction among the molecules. One molecule is not attracting the other or not repelling the other molecule. So there is no interaction between two molecules of the gas until or unless they collide with each other or they collide with the walls of the container. Otherwise, the molecule is freely moving inside the container. It does not experience any kind of force except during the collision. So for an ideal gas, there is no interaction between the molecules. This is a very important condition for a gas to be ideal, that molecules of the gas does not experience any force of attraction among them between two molecules or any force of repulsion. They do not interact with each other because the size of the container is very large. The molecules are at a distance such that they do not interact with each other until or unless they collide with each other. So during the collision, there is a force experienced by one molecule due to the other, or when a molecule collide with the wall, there is a force experienced by the molecule during the collision with the wall. So basically these all the postulates are some way supporting each other. Like first one, we defined this small term. So this is only possible when the container size is very large as compared to the total volume of the molecules or volume of the molecules. So as compared to the molecule volume, the container should be very large. That's why the molecules are not interacting with each other. The distance between the molecule is again large because the size of the container is large. This term will also come into the picture. Spherical we are just taking we are understanding a most simplified gas that have spherical molecules, and those are called the atoms. And elastic, we are not considering any kind of energy loss during the collision. So second postulate was they all move in the randomly in all the direction without giving any preference to any particular direction. Distribution is uniform. Molecules distribution and the velocity distribution is uniform, and these molecules do not exert any kind of force on each other except during collision. Are these 4 postulates clear to all of you? Is there any kind of confusion in this postulate? Any kind of confusion? If there is any confusion, I'll definitely explain it. Second point is the distribution of the molecules. The molecules are uniformly distributed inside the container. Their velocity distribution is also uniform. So suppose you take a volume dV volume at one corner of the container. At the other corner, you take the same volume dV. So suppose 5 molecules in the first volume are moving towards left, then you treat that 5 molecules are moving towards left in the lower dV volume as well. So the velocity distribution is uniform. Okay, the velocity distribution is uniform and the molecule distribution is also uniform. So these were the 4 postulates. Next one is the collision of the molecules with each other and with the walls of the container are elastic. The collision of the molecules with each other and with the walls of the container are elastic. That we have already, because we are taking elastic molecule, so collision will be elastic. There is no loss of energy during the collision. The duration of collision is much smaller than the time interval between the 2 successive collisions. The duration of collision is much smaller than the time interval. Obviously, so basically they are saying when a molecule is moving, it is free. It does not experience any kind of force. When it collide with another molecule or with the walls of the container, that duration is very small. So you are treating that molecule, except that collision, you are treating that molecule as a freely in motion. So that the force is not there for very long time. So the collision of the molecule with each other and the walls of the container are elastic, and the duration of the collision is much smaller than the time interval between the two successive collisions. See, I am spending more time on these postulates so that you get time to note them down. So you start writing these postulates, you have sufficient time, because I am multiple time explaining these postulates. So you write, you make notes of whatever content I am covering. I'll provide this PDF as well, but if you write by your own, that will stay longer in your memory. That happen actually. So the next postulate is, the motion of the molecules is governed by the Newton's laws of motion, and gravity has no significant effect on the behavior and the parameters of the gas. So you'll say, sir, whenever there is a container, a force on each molecule is acting downward, that is the mg. So will gravity have any kind of effect on them? So we are not considering any significant effect of the gravity on the behavior and the parameters of the gas. And these motion of the molecule is again governed by the Newton's laws of motion. So when the molecule is in motion, it is moving freely in a straight line until it collide with any other molecule or the walls of the container. So no force is acting on it. The motion is uniformly moving in the straight line, but after the collision, the direction of the molecule changes. So 4 plus 2, 6 postulates we have already covered. There is no fixed number of the postulates. See, there is no fixed number like this many postulates are there. No, it is not like that. There are certain assumptions, conditions or postulates which make us understand a gas. Like whatever discussion we are going to do in this topic, that will be based on these postulates. We will be taking them as a base. We will consider them as a base, and then we will talk about the other parameters of the gas. Like this, there is one thing we talked about. The molecule exert no force on each other and walls of the container except during the collision. This postulate plays a very important role. You know, there is a term which is called the potential energy, and that potential energy term is the cause of potential energy. What are the forces which contribute to the potential energy? Those are internal conservative forces. So when there is a system and there are internal conservative forces, they can contribute to the potential energy. So in the one postulate we have considered that molecules are not interacting with each other, so there is no potential energy term. So when we are talking about the kinetic energy of the gas, we are understanding the energy of the gas. We don't have to talk about the potential energy of the gas. So these postulates will help us in understanding the gas. I told you in beginning, these are the postulates, these are the assumptions which make us understand the gas properly. Let's move to the next postulate. Motion of the gas molecule freezes at 0 Kelvin temperature. I hope you all are aware of it. At 0 Kelvin temperature, we consider the gas molecules are not in motion. The path traveled by the molecules between two collisions is called the free path. The path traveled by the molecules between two collisions is called the free path. And the mean of this distance, or the mean of the distance covered between two collisions, is called the by a molecule is called the mean free path. The derivation of mean free path we will do in the end of this topic. So this is called the mean free path, and mean free path is also in your syllabus. On what parameters mean free path depends, those we will talk about. So a molecule is in motion, it collides with another molecule or the walls of the container. So before that collision, some distance is traveled by the molecule, that free distance traveled by the molecule. So it will have so many values. So we take the mean or average of those distances, and that is called the mean free path. So mean free path is basically the average of the distances traveled by the molecule between two collisions. a gas at very high temperature and low pressure can be treated an ideal gas. A gas at very high temperature and the low pressure can be treated like an ideal gas. So this is the last one is a very important assumption. Sometimes they directly ask in the question, okay, what are the condition of foreign gas to be treated like an ideal gas? So high temperature, high pressure, low temperature, low pressure, low temperature, high pressure, high temperature, low pressure. So they make 4 options. And if you understand this, at very high temperature and low pressure, a gas can be treated like an ideal gas. High temperature, low pressure. So temperature and low pressure. So you all are aware of an ideal gas equation. Ideal gas equation PV equal to nRT. So volume of the container should be large, so there is no interaction between the molecules. So volume should be large. So the conditions favoring a large volume will be the condition favoring the ideal gas. So when pressure is low, P into V equal to nRT. And temperature is high, pressure is low. PV side, pressure is low. On the other side, temperature is high. The volume will be high. Product of PV equal to nRT. So volume, high volume will favor the ideal gas. It will favor an ideal gas condition. Okay. So these all are the postulate for an ideal gas in a steady state. In a steady state, these are the postulate which we will be taking in consideration when we move further in this chapter. So are you able to understand all the postulate of the ideal gas? Are all the postulate of the ideal gas clear to all of you? All the postulates of the ideal gas clear to all of you? So there is one very important term, and that is called the root mean square speed, VRMS. You all have studied it. You all remember the formula, and most of the question are asked on the RMS speed only. This is so important. This concept is so important that out of if they ask 10 question on KTG, so 5 to 6 question will be related to the VRMS, or 7 question will be related to the VRMS or average speed or most probable speed. This is so important. Sometimes they ask a question comparing RMS speed of the molecule with the sound speed of the sound, that is root can the gamma RT by M. There is a formula that we study before the thermodynamics. So this is so important. This topic is this part of this KTG is so important. So we are going to understand what is VRMS, what is root mean square speed. So this definition is not the technical definition. This definition is given by me. Like this way you can easily understand what is the meaning of the RMS speed. So from beginning we are saying gas is a collection of the large number of molecules. They are in the random motion. Random motion means they don't have a particular velocity. They don't have a particular speed. They all can have random speed. They are randomly moving. The direction is not fixed. They are randomly moving with the random speed. So we define a speed that is called the RMS speed. What is the meaning of RMS speed? So if you say, okay, all these molecules are in the random motion. They all have random speed. Okay. I want to give them a particular speed to all of them. I want they should have same speed. If they should have same speed and their kinetic energy is equal to the actual kinetic energy, then the same speed given to all the molecules is called the RMS speed. Are you able to understand the RMS speed or significance of the RMS speed? So what is the significance of the RMS speed? So RMS speed is the speed if this speed is given to all the molecules, only this speed, the same speed given to all the molecules, their actual kinetic energy is equal to the kinetic energy corresponding to the RMS speed given to all the molecules. So again I explain it one more time. So suppose there are 5 molecules. One is moving with V, another moving with 2V, 3V, 4V, 5V, 6V, or the 5V. So all are moving with V, 2V, 3V, 4V, 5V. 5 molecules are moving with this speed. So they have different speed. So there will be kinetic energy, total kinetic energy of these 5 molecules. How do we write the total kinetic energy of all the molecules? Half m v square, half m 2v chi square, half m 3v chi square, half m 4v chi square, half m 5v chi square. So we get the total energy of the gas. Okay, total kinetic energy. Now I say I'm going to give a uniform speed to all the molecules. I'm not giving v, 2v, 3v, 4v, 5v. No, I'll give same speed. I'm not saying same velocity. Velocity means you are also giving the direction also, same direction. No, I'm saying I'm giving the same speed to these 5 molecules and their kinetic energy matches with the actual kinetic energy. Then the same speed given to all the molecule is called the RMS speed. Are you able to understand RMS speed? I hope first time this RMS speed concept is clear to you. Is this clear to you? What is the significance of the RMS speed? So it is basically a speed. If you give this speed to all the molecules, the total energy of the gas remains same. Total energy of the gas is actually equal to the total energy of the gas is equal to the actual energy of the gas. Clear? So how do we define this? So I say translational kinetic energy of the gas. Translational kinetic energy. Translational kinetic energy of gas. What will be the translational kinetic energy of the gas? Half mv1 ka square, half mv2 ka square, and so on. Molecules, they all are identical, so their mass will be same. Mass of the first molecule will be m, second molecule will be m, third molecule will be m. Speed of the first molecule is v1, v2, v3, and so on. So this is the actual translational kinetic energy of the gas. Now we give RMS speed to all the molecules. We give a speed to all the molecules and we say, take this speed and your total kinetic energy is equal to actual kinetic energy. Then that speed is called the RMS speed. So now we are writing this translational kinetic energy like this. Half m into Vrms square, half small m into Vrms square, okay, and so on. So there are total n molecules, so there will be n terms. So we are comparing both the energies, like we say this energy is equal to that energy, actual energy. So n into half m into Vrms square, this is the total translational kinetic energy. Okay, capital N into m becomes the total mass of the gas. There are total n molecules, m is the mass of each molecule, so this becomes half capital M into Vrms square. This is the total translational kinetic energy of gas. So you can directly write translational kinetic energy of the gas if you already know the RMS speed of the gas. So half m into Vrms square is equal to total translational kinetic energy of the gas. Okay. Now we equate both the terms, this one with this, because this term we got from here. Okay, we added all the terms, n terms, so n times of this. So half n into m Vrms square is equal to, can I write half m summation of Vi square, I equal to 1 to I equal to n. Can I write this part like that? Half m we can take out. This will be equal to v1 square plus v2 square plus v3 square. So v1 square plus v2 square plus v3 square. M gets cancel out, 2 gets cancel out. So Vrms square is equal to summation of all the square of all the speeds divided by n. divided by n. So this is basically average of square of the speeds. So VRMS square is equal to, you can write like this. This represent the average. So we are writing the average of a square of the speeds. So every molecule has different speed. We square those speeds and take average of them. That is there. So VRMS is equal to root over V square. This is VRMS. This is VRMS. So what are we doing here is, we are first, this is basically, we can write it like that. We square all the speeds and take mean of those speeds and then a root, and you get the VRMS. So what you have to do to get the VRMS, you square all the speeds, you take mean of them, and then root of them is the VRMS. What is the significance and what is the formula of VRMS? Are you able to understand? How do you find the RMS speed of the gas molecules? Yes, it is the same thing. Like I can write here. So VRMS is equal to root over V1 square, V2 square, and so on divided by n. This is the same formula. This is the same formula. We are squaring the speeds, adding them, and then taking their mean. We are taking mean of the square of the speed and then taking the root, and that is the VRMS. So VRMS is V1 square plus V2 square plus V3 square and so on divided by n. This is the VRMS. See, for the NEET students, this is more than sufficient. Like, this is more than sufficient. I have to add something for all the students. If there is any student for the JEE, just 2 lines I'll write. There is one very important formula. If relation between dV and dN is given, sometimes this will not be asked in the NEET, or just take the, just write this for as an information. Sometimes this kind of function is given. dV by dN is given as function of the velocity. They should not ask in the NEET, but for the safe side I am covering this, because this is in part of the JEE main, and a simplified question can be made for NEET as well. So whenever you find this relation dV and dN, so VRMS, you write VRMS square, you write like V square dN divided by n. This is one more formula which you have to keep in mind. There is one more formula for average. When average speed is, you have to calculate, so you write V dV divided by n. This is the average speed formula. These two formula are mainly important for if any student of JEE is watching this video, then they can keep these formulas in mind. These are the two very important formulas. But when you have to apply these formulas, when relation between dV and dN is given. Okay. So is this clear to all of you? Root mean square speed or VRMS. Let's move to let's understand the pressure of the gas inside the container. How does a gas exert a force on the walls of the container, or the gas pressure is defined in, if a gas is enclosed in the container. And what is the relation between gas pressure and the RMS speed? Because to understand the energy of the gas, see, there is one, there is very important term I told you in beginning. KTG is going to help us in finding the internal energy of the gas. That internal energy of the gas and the change in the internal energy of the gas we will use in thermodynamic processes. You all are familiar with the equation delta Q is equal to delta U plus ka W. In chemistry you use minus, don't worry about that, I'll make that clear as well. Delta Q is equal to delta U plus ka W. This delta U, you will understand from here. So I have already talked about the internal energy or the translational kinetic energy of the gas. The translational kinetic energy of the gas depends on the RMS speed. Do you remember any question you have seen that write down the, you are solving a thermodynamic question and the RMS speed is given and you are calculating the internal energy using RMS speed? No. Mostly about the gas, its pressure, temperature and volume are given. Number of moles are given. So we have to relate this translational kinetic energy with its pressure, volume. So that relation we are going to establish while deriving the pressure of the gas inside the container. So whenever you write the internal energy of the gas, so we have till now we have considered the gas to be spherical. So we are not going to talk about the vibrational energy, we are not going to talk about the rotational energy. The gas will have only translational energy, and we are able to calculate the translational energy in terms of the RMS speed. But we don't know the relation of the RMS speed and the pressure of the gas and the volume of the gas and the temperature of the gas. Then how we are going to write the total translational kinetic energy of the gas or the internal energy of that gas? So to write the internal energy of the gas, we have to establish a relationship between Vrms and the pressure of the gas inside the container. So many of you have thought about this, like when you studied this topic, you might have confusion about this, why we are doing this derivations. They all are interlinked. Are you able to relate that? Like the way I am relating, are you able to understand that? What did I say? Again, I'm going to repeat the statement. See, KTG is not that difficult, but we don't spend time with this topic, and that's why this topic seems us to be difficult. So in kinetic theory of gas, we said molecules does not have any kind of interaction. So when you are talking about there is a container and inside that container there is a gas and you want to study its internal energy, there is no interaction, so there is no potential energy inside. Okay, what kind of energy is there? There is a kinetic energy only. So kinetic energy also has some types, like translational kinetic energy, molecule is moving, rotational energy, vibrational energy. But our discussion is limited to monoatomic gas because we are taking spherical molecule and that molecule is small as well. We are not going to talk about the rotational energy. We are not going to talk about the vibrational energy. So like our discussion till now is about the monoatomic gas. So monoatomic gas can only have translational kinetic energy. So kind of we are defining the internal energy of the monoatomic gas like translational kinetic energy of the gas, and that translational kinetic energy, which is the internal energy of the monoatomic gas, is equal to half mass of the gas into Vrms ka square. But again, we don't know how to relate Vrms with pressure, volume and temperature of the gas. So either Vrms should be given to us then you can write the internal energy of the monoatomic gas. But in most of the question, it is not the case. In most of the questions, what is given to us? Pressure is given to us, temperature is given to us, volume is given to us, and we have to find the internal energy of the gas, whether it is monoatomic. Later we generalize this discussion to diatomic and triatomic as well. But till now, we are talking about a gas which has a spherical molecule, and that is the monoatomic gas. We can directly say that we are talking about the monoatomic gas. Is this clear to all of you? So what is our next goal? We have to relate Vrms with pressure, temperature and volume. Yes, we are not going to talk about the ideal gas equation, which is PV equal to nRT. The relation between pressure, volume, moles and temperature is already there. We all know that. So we are not going to talk about that. So if we are able to relate RMS speed with pressure, then we can easily relate it with temperature as well. Got it? Clear? Clear? Why are we doing this discussion? So pressure of the gas inside the container we have to talk about. So what is pressure? So pressure is, there are walls of the container. I have taken a container. Suppose this side is L, this side is B, and this side is H. I am taking this cross section, and let's say this is PQ R S. This surface area I am taking. So the force exerted by gas on this per unit area. So the area will be, what is the area of this surface? H into B will be the pressure inside, or pressure of the gas. So just take any surface, any face of this, and calculate the force on that face and divide that face force by area. You get the pressure, inside pressure, and the pressure will be uniform throughout, because we have considered uniformity in the gas, the uniformity in the speed, uniformity in the molecule distribution, everything we have taken as uniform. So force per unit area is the pressure. So we have to just calculate the force exerted on a wall by the gas molecules, and that force per unit area is the pressure. Clear? Okay. So this is the surface. See, one more thing. If there is any surface and a particle of mass m strikes this surface with v speed or v naught speed elastically, if it strike elastically, it will rebound with the same speed. The momentum imparted by this molecule, yeah, this particle will be 2mv naught. Are you all aware of this equation? The molecule, this molecule will impart momentum is equal to 2mv naught. Delta P is 2mv naught. And momentum transferred per second is equal to momentum transferred per second is the average force. This is the definition of the average force acting on this surface. So if multiple molecules are striking on this surface, then in 1 second the number of the momentum transferred to the surface is called the average force. Average force definition clear to all of you? Okay. Or you could say, let's say, or n molecules strike in delta t time. Let's say n molecules strikes in delta t time. Then average force will be n into 2mv naught. This is the momentum transferred, and this momentum is transferred in delta t time. So momentum transferred divided by delta t is the average force will be acting on that surface. So this is additional information. This is not from this topic. This is definition. This part is from center of mass part. Okay. So this clear to all of you? So average force is calculated like this. You take a surface, you check what is the momentum transferred by one molecule, and then you say in delta t time the momentum transferred by all the molecule is, if delta p, then delta p by delta t is the average force. Okay. So let's say there is a molecule traveling with v1 speed. So it will not be in this direction only. In this direction, the speed of this molecule is v1x. It has speed in this direction as well. It has a speed in this direction as well. Suppose this is the molecule of mass m and it is moving like this. So it will be going towards this with this speed. This is the speed with which it is going towards the surface. When this molecule strikes this surface, and there are certain parameters. See, small m is the mass of each molecules. Mass of each molecule, we are writing it small m. Capital N is the number of molecules, total number of molecules. Okay. Capital M is the capital N into m, and this is the mass of gas. Mass of gas. And we will write m naught, that is the molar mass. We will represent molar mass with m naught. Molar mass of gas with m naught. So these are the like certain parameters we will use while deriving the pressure of the gas inside the container. So m naught we have, m we have, these all we have. So this molecule will strikes the wall of this container. This molecule moving in this direction with v1x, in this direction with v1y, and in this direction v1z. So when it strikes with the wall, this component will get reversed. It will become v1x. This will remain unaffected. v1y, v1z, they won't change. v1z and v1y will not change because they are parallel to this surface. So when it strikes the wall of the container, normal will act on this particle. Normal force will act on this molecule. There is no friction. So only friction can change the velocities along the surface. So normal force will reverse this component. So the momentum transferred by this molecule, delta P1, will be equal to 2m v1x. This is the momentum transferred by this molecule on the this is the momentum transferred by this molecule. Now this molecule will go towards this wall. It will strike here, and again this component will get reversed, and again it will go to the wall, same wall. So the time interval when the same velocity molecule strikes this wall is equal to 2L divided by v1x. Is this clear to you? Molecule with x component is equal to v1x will go here and then again come to this wall. So after this interval of time, a molecule with v1x x component of the velocity will strike the wall. So average force imparted by the molecule of v1x velocity, or you say the x component of velocity v1x, the average force imparted by this velocity molecule is equal to, so F1, we are calling it F1 average, will be equal to 2m v1x. This is the momentum transferred in each collision, and what is the interval after which it is colliding again and again to the wall? That is 2L divided by v1x. So after this interval, this much momentum is transferred by molecule which has x component of velocity equal to v1x. Is this clear? This clear to all of you? So this is the average force by one molecule, and this comes out to be m v1x square divided by L. So this is the average force by one molecule. So what is the total force? There are so many molecules. We only talked about one molecule. There are n molecules. So F net is equal to m divided by L. We will take common, then it is equal to v1x square, v2x square, v3x square, and so on. We'll write like this. And if we multiply this with n, and divide with capital N, this becomes capital M. So net force is equal to total mass of the gas divided by length, and this becomes average of Vx square. So this is the average of square of the x components. So this expression we get from here. This expression we get from here. So this force is equal to m Vx square average divided by L. This is the net force on this surface. What is this term? This is the average of only x component, square of the x components. So every molecule has a x, y and z component. So their x, what we are doing? We are doing the square of the x components. So we are taking x components of the molecules, we are doing the square and taking average, we are getting the net force. Now again there is a problem. Again this cannot be related to VRMS. How do we relate this with VRMS? Let's talk about it. So every molecule, let's say first molecule, the velocity of the first molecule, V1 vector, can be written like V1x I cap, V1y j cap, V1z k cap. This is the velocity of first molecule. Similarly, velocity vector of the second molecule will be V2x I cap, V2y j cap, V2z k cap. This way we can write the velocity of all the molecules. Okay, so these are the velocity of all the molecules. Now if I want to write the V1 square, will it be equal to V1x square, V1y square, V1z square? If I want to write the speed, the magnitude of this vector, so V1 square is equal to V1x square plus V1y square plus V1z square. V2 square will be V2x square, V2y square, V2z square, and so on. Okay. There we get square of all the velocities. There we get square of all the x component. There will we get sum of the square of all the y component, sum of square of all the z component. Clear? If we divide this by n, this also by n, this also by n, this also by n, we get v square average. This is Vx square average, Vy square average, Vz square average. We get this relation. Yes. Now there is a relation between these two, and this root of this thing is VRMS. Now we are able to relate these. Acha, molecules are not giving any preference to any direction. So square of all the x component average will be equal to square of average of the square of the y components will also be equal to average of square of the z component. So these three terms will be equal. So you can write square of v square, the average of v square is equal to 3 times Vx square. So this Vx square average comes out to be v square divided by 3. Okay, this we got. What was our force? Force was m upon L into Vx square. So net force on ABCD, was it ABCD? No, PQRS. PQRS is equal to m upon L, this square, which comes out to be v square divided by 3. And if you remember this, VRMS square is equal to v square. So this force on PQRS surface can be written like m upon L VRMS square divided by 3. This is very, very difficult expression for the pressure, and if you are able to understand it, then you have really worked hard, or you understand the physics. Otherwise there is a direct formula. I'll tell you, you can keep that in mind. Pressure is given by F on PQRS divided by B into H. So this will be M divided by L into B into H. VRMS square divided by 3. Can we write like this? What is this? This is the total volume of the container and this is the total mass of the gas. Mass divided by volume is the density. So we get pressure is equal to rho into VRMS square divided by 3, or VRMS is equal to 3P divided by rho. So there is a relation between VRMS and the pressure, and if we have this relation, now we can relate the energy, the translational kinetic energy of the gas with pressure, because now we are able to relate the VRMS with pressure. No, root. There will be root of this. Got this? VRMS is equal to root over 3P divided by rho. Root over 3P divided by rho. Root over 3P divided by rho. Clear? Is this clear to all of you? Is this clear to all of you? Now, VRMS, we have root over 3P divided by rho. There is ideal gas equation PV equal to nRT, or it can be written like P equal to rho RT divided by M naught. So P divided by rho is equal to RT divided by M naught. So VRMS can also be related with the temperature, and that is the 3RT divided by M naught. So for a gas, VRMS is directly proportional to root over T. This is the relation between VRMS and the temperature. Total translational kinetic energy. Total translational kinetic energy. Total translational kinetic energy of the gas is equal to half mass of the gas into VRMS square. This is the total translational kinetic energy of the gas. Translational, I am saying translational only. So TTKE, when I am writing TTKE, so okay, when I say I'm talking about the kinetic energy, then always think about the translational, okay? So this kinetic energy, if this energy I represent with E, so E is equal to half M into VRMS ka square, that is 3RT divided by M naught, which is equal to 3/2 nRT. This is the total translational kinetic energy of the gas. Or you can write this energy is equal to 3/2 PV. This energy density you get, energy density is equal to 3/2 P. This is the translational, okay? Got it? Because till now we haven't talked about vibrational or rotational energies, kinetic energies. Clear? Is this clear to all of you? Translational kinetic energy. See, my way of teaching is quite different from the others, and I hope you are first time getting this much information about any topic. This will happen in my classes, but after my classes you will be able to solve material of any institute, any coaching. You will you will not find any difficulty in solving that material. Never. You will never find that difficulty. That is the beauty of my lectures. That is the beauty of my lectures. But there is a problem. You might have to watch this lecture twice. If you want to completely understand the lecture, you will have to watch it again one more time, and then everything will be clear to you like clean water, you know. You will be able to see each and everything. You will be able to relate each and everything. What is the weightage of this chapter? There like one question from this part and one question you can expect from the thermodynamics part. Where this part is very important. KTG, thermodynamics, calorimetry, heat transfer, and all these topics. Okay, so energy part is done. Total translation kinetic energy part is done. VRMS and this all is done. So this is the relation between VRMS and pressure. So root under 3RT divided by m0 is the RMS speed. So finally we write RMS speed is equal to, so there are two formulas of the RMS speed. RT divided by m0 or VRMS is equal to 3P divided by rho. Okay. So let's solve a question on this. Are we able to solve a question of RMS speed or not? So there is this question: RMS speed of the nitrogen gas at 27 degrees Celsius is approximately equal to. So you have to find the RMS speed of the nitrogen gas at 27 degrees Celsius. There is one more option, and that option is E, which says none of these. So there is one more fifth option that says none of these is the correct option. So RMS speed of the nitrogen gas at N2 gas, nitrogen gas, which is the N2 gas, at 27 degrees Celsius is approximately equal to. Can you find the RMS speed of the nitrogen gas at 27 degrees Celsius? At 27 degrees Celsius, can you find the RMS speed of the gas? Guys, do not forget to like the session if you like it already. If you already like it, then please like it. If you don't like it, then it is fine. Otherwise, you should like it. Okay. So what is the RMS speed of the nitrogen gas at 27 degrees Celsius? Approximately equal to. Can you solve a simple question of RMS speed? Guys, believe me, you might commit a mistake in this question as well. If you try to solve, there are high chances that you will not be able to find the RMS speed of the nitrogen gas at 27 degrees Celsius. Try to solve this question. Can you solve this simple question? Can you find the answer? I'm waiting, guys. Please try to solve this question before I solve. So one student has answered E option, the other also answered E option. One student C option, E option. So E is dominating. E option is dominating till now. Some has Google searched it. 516 is given on the Google. So there is no option. Why are you writing 516? So E option. So approximately, like there is a plus minus 5 meter per second is fine. That other option I have given due to some other reason. Okay, you have already done this question. Huh? So what kind of mistake we commit while solving this question? This question is very easy. Formula we all know. Still, I am saying that there are highly chances the student commit the mistake. The formula of VRMS is root over 3 RT divided by M naught. So first we have to convert this in Kelvin. It is 300 Kelvin. Okay. Value of R is 25 divided by 3 approximately into T, which is 300, divided by the molar mass of nitrogen gas is 28, and sometimes we forget that this 28 is in gram. This is the mistake most of us commit. This is not in kilogram. We have to put everything in the SI unit here. So we have to multiply. We forget to multiply this. This is the mistake I have seen most of the student committing. So when you solve this, this comes out to be 518 meter per second. So this option I gave you because there are chances if somebody misses this, he will get a very different answer. Because of that, I gave the E option. So the approximately equal to 520 meter per second. Okay, is this clear to you? Clear to all of you? There is no such problem on my side, like whatever problem you are facing, it's working fine in my laptop. No such problem is there. This question clear to you? RMS speed of the nitrogen gas at 27 degrees Celsius is approximately equal to this. Now let us talk about the internal energy of the monoatomic gas. Guys, one by one we are going to clear concepts. So we started from the postulates. We went into the translational kinetic energy part. There we find a problem that translational kinetic energy was related to RMS speed. It was not related to pressure, volume and the temperature. Then we find a relation between VRMS and the pressure and the temperature. Now we are able to write the translational kinetic energy of the gas in terms of pressure or density or temperature. Yes, there is some kind of lag. I have already explained the derivation part as well. This derivation, I derived this in the class only. Which part? This question. You have to put this mass, molar mass in gram. That was the question. Oh, it will be 3 RT divided by M. Now you will get 518. Got it? Let's talk about the internal energy of the monoatomic ideal gas. So monoatomic gas only has translational kinetic energy. Translational kinetic energy. There is no interaction. There is no interaction between molecules. Hence, no interaction potential energy is there. Interaction potential energy is there. So there is no interaction between the molecules, hence no interaction potential energy is there. So internal energy of monoatomic gas, is equal to translational kinetic energy. So internal energy of the monoatomic gas is equal to translational kinetic energy. So monoatomic gas has internal energy equal to translational kinetic energy. So U of monoatomic gas is equal to 1 by 2 m into Vrms square. If you put the value of Vrms, it is equal to 3 by 2 PV or 3 by 2 nRT. So now you are able to find the internal energy of the monoatomic gas, and that is equal to 3 by 2 nRT. Is this clear to all of you? So internal energy of the monoatomic gas is equal to 3 by 2 nRT. Internal energy of the monoatomic gas is equal to 3 by 2 nRT or 3 by 2 PV, or U of the monoatomic gas is equal to 3 by 2 PV. So if you know the number of moles, temperature of the gas, you can write the internal energy of the monoatomic gas. So U of monoatomic gas is equal to 3 by 2 P into V. Is this clear to you? The internal energy of the monoatomic gas is clear to all of you? Is this clear to all of you? Monoatomic gas internal energy. Monoatomic gas internal energy. Done? So can we write the internal energy of the diatomic gas and polyatomic gas? Yes. But in diatomic gas and polyatomic gas, there are, apart from the translational motion, there is vibrational motion, rotational motion also. So we need to consider that energy as well. So for the same temperature, for the same number of moles, the energy of diatomic and triatomic or polyatomic gas will be more than monoatomic gas, because apart from this translational wala term, there will be rotational and vibrational energies as well. So we need to find rotational and the vibrational energy of the diatomic and triatomic gases. So for that, we have to cover the topic or concept of degrees of freedom, DOF, degree of freedom. So what is degrees of freedom? Different type of, so after studying this part, we will be able to find the internal energy of any ideal gas. We will be able to write the internal energy of any ideal gas if temperature of that gas is known and the number of moles of that gas is known. So degrees of freedom, different types or number of ways a gas molecule can have energy are called degrees of freedom. So gas molecule, the number of ways or the number of ways or different types a gas molecule can have the energy are called the degrees of freedom. So translational degrees of freedom, maximum possible. So in translational kinetic energy, translational kinetic energy of the molecule can be written like half m Vx square, half m Vy square, half m Vz square. It can have three terms. So maximum translational degree of freedom will be equal to 3. Translational degrees of freedom will be equal to 3. So 3 is the maximum translational degrees of freedom. So any gas molecules can have maximum 3 translational degrees of freedom. Okay, is this clear to all of you? So maximum possible degrees of freedom, translational degrees of freedom are 3. Rotational degrees of freedom. So rotational kinetic energy, it can also have 3 terms. The molecule might rotate about x-axis, it might rotate about y-axis, it might rotate about z-axis. So it can have 3 degrees of freedom. So maximum rotational degrees of freedom are also equal to 3. So maximum rotational degrees of freedom are also equal to 3. So 3 degrees of freedom maximum can be there. Rotational degrees of freedom 3 can be there. Vibrational degrees of freedom. So during vibration the energy can have 2 values. This is the vibrational degrees of freedom are, so vibrational energy have 2 values, vibrational kinetic plus potential. So in one direction it can have vibrational degrees of freedom equal to equal to 2. So 2 can be the vibrational degrees of freedom. So rotational degrees of freedom, vibrational degrees of freedom, and the translational degrees of freedom. So 3 maximum possible translational degree of freedom, 3 rotational degrees of freedom, and vibrational degrees of freedom will be 2 in one direction. Degrees of freedom of the monoatomic gas. So in case of monoatomic gas, degrees of freedom will be equal to 3, and they all are translational only. So degrees of freedom in case of monoatomic gas will be equal to 3, and they all are translational. Degrees of freedom in case of the diatomic gas, degrees of freedom is represented by F, will be equal to 5 at normal temperature. F becomes 7 at high temperature, and if we consider vibrational degrees of freedom, so sometimes it is mentioned that vibrational degrees of freedom you have to consider, and F becomes 3 at very high temperature. Molecules dissociate. So if a molecule dissociate into atoms, then degrees of freedom will become 3. So these are the degrees of freedom for the diatomic gas. F is equal to 3 at very high temperature when molecules are dissociated. Triatomic or polyatomic gas, if linear, see these 5 are 3 translational plus 2 rotational. These 7 are 3 translational, 2 rotational plus 2 vibrational, and these 3 are all 3 translational. So if molecule is linear, degrees of freedom will be 5, 3 translational, 2 rotational. If non-linear molecule is there, degree of freedom will be 6, 3 translational and 3 rotational. This is all about the degrees of freedom. So degrees of freedom will be In case of monatomic gas, 3 degree of freedom. Diatomic gas at normal temperature, we generally consider 5. At very low temperature, the rotational energy is low. In that case, the diatomic gas will have 3 degree of freedom at temperature less than 70 Kelvin. Temperature less than 70 Kelvin, the diatomic gas also has 3 degree of freedom, only translational. The rotational part, the rotational energy is very small in that case. So in that case, there will be 3 degrees of freedom of the diatomic gas. 5 for at the normal temperature, 7 at the high temperature, and the 3 again at the very high temperature, the molecule dissociate. So this is all about degrees of freedom. Are you able to understand the degrees of freedom? So there is a very important law. That is called the law of equipartition of energy. We can understand by the name that it talk about the equipartition. So we equally divide energy, but based on what? That we are going to discuss here. According to this law, the total energy of a molecule, first of all, understand this law talks about the molecule. The total energy of the molecule is equally distributed among all of its degrees of freedom. So they are saying that total energy of a molecule is equally distributed among all of its degrees of freedom. Okay. So let's say, and they have given this, energy of a molecule associated with each degree of freedom is equal to 1 by 2 kT. Energy of each molecule associated with each degree of freedom. Average energy of molecule associated with each degree of freedom is equal to 1 by 2 kT. It does not depend on the molecule. It only depends on the temperature. But remember, this is the average energy of each molecule. Average energy of each molecule corresponding to each degree of freedom, and that is equal to 1 by 2 kT. K is a Boltzmann constant, and this does not depend on the gas. Which gas is this? It does not depend. So can we derive this? Yes, in this part we will derive it. You know, monoatomic gas has 3 degree of freedom, and we know U of the monoatomic gas, that was 3 by 2 nRT. Okay, if n moles are there. So kinetic energy of molecule, वो भी translational kinetic energy. Okay, because this is the translational kinetic energy only. So there are Na molecules. So we divide this with n. So this becomes 3 by 2 n divided by total number of molecules, because there are capital N molecules and the energy is this. If we divide this with n, so the energy of each molecule we are getting. R is equal to Na into Boltzmann constant into T. See, number of moles is n divided by Na. So this into this is cancel out by this. So this comes out to be 3 by 2 kT. So the average translational kinetic energy of each molecule is equal to 3 by 2 kT. Okay, it is equal to 3 by 2 kT. But there is a problem. Translational degree of freedom are 3. So it is total translational energy of each molecule 3 by 2 kT. So if we equally divide this translational kinetic energy into each degree of freedom, then we will divide that by 3. We will get 1 by 2 kT. So average kinetic energy of each molecule corresponding to each degree of freedom is equal to 1 by 2 kT, and this does not depend on what? This does not depend on the type of the gas. It only depends on the temperature. Clear to all of you? So can we write energy of a molecule associated with F degrees of freedom, it will become F by 2 kT. Is this correct? Energy of a molecule associated with F degree of freedom. 1 degree of freedom, 1 by 2 kT. F degree of freedom, F by 2 kT. Energy of Na molecules with F degrees of freedom will be F by 2 Na into kT. Na molecules means 1 mole. So energy of 1 mole of gas with F degree of freedom, F by 2 RT, Na into K is R. Energy of N moles of gas with F degrees of freedom is equal to F by 2 nRT. See, now we are able to find the internal energy of monoatomic and diatomic gases as well. So monoatomic we already know. So U of monoatomic is 3 by 2 nRT. U of any other gas F by 2 nRT. For monoatomic gas, F is equal to 3 and it was only translational energy, but other gases degree of freedom will include the other type of kinetic energy, vibrational, rotational, and every energy will be involved because of there is F. F include all the possible form of energy. So any gas will have energy equal to internal energy of an ideal gas is equal to F by 2 nRT. So our discussion is limited to only ideal gas, and the energy of ideal gas is equal to F by 2 nRT. So this law of equipartition of energy and the understanding of the degrees of freedom help us in obtaining an expression of internal energy of the gas. F for triatomic, 5 is for linear and 6 for the non-linear. Yes. So now energy of any gas of n moles having F degrees of freedom is equal to F by 2 nRT. So now you can write energy of any gas U of monoatomic is equal to 3 by 2 nRT. Purely translational. Monatomic gas has only translational kinetic energy. U of diatomic 5 by 2 nRT. So 3 by 2 nRT is translational kinetic energy plus 2 by 2 nRT is the rotational kinetic energy. So if they ask the ratio of translational kinetic energy to rotational kinetic energy, you must be able to write. Clear? And same for polyatomic or other gases we can do. But now we are able to write the energy of the internal energy of the ideal gas F/2 nRT. So this is a very simple formula we are going to use. If you change the temperature during any process, temperature changes, then delta U will change and it will be equal to F/2 nR delta T. So in the next topic, which is the thermodynamics, we will be talking about change in the internal energy. And the change in the internal energy can be found with the help of this formula. And this formula is about the change in the internal energy of the gas. So change in the internal energy of the gas can be found out. If you know the type of the gas, it is monoatomic or diatomic, you know the temperature may change and moles of the gas, the first part of the first law of thermodynamics is done. So you all are aware of the first law of thermodynamics. There is a expression delta Q in any process. Delta Q is equal to delta U plus ka W. So delta U you will be able to find with the help of this formula. Okay, there is one more formula of delta U. रट लेना इस फॉर्मूले को. So delta U is equal to F/2 P final V final minus P initial V initial. There are these 2-3 formulas of delta U. Delta U is given by these formulas. So with the help of kinetic theory of gas, one term we are able to find if pressure, volume, temperature are given for a gas, we can directly find what is the change in the internal energy of the gas during this process. Yes, F/2 PV. You can write this like F/2 PV. I used to face a lot of difficulty in differentiating these terms. Nobody told me that clear that you don't have to worry about internal energy. Internal energy, it is you can directly write F/2 nRT, F/2 PV. You know the type of gas, you just identified the term. Is it monoatomic or diatomic? You know the degree of freedom. If number of moles and temperature is given, use nRT wala formula. If pressure and volume is given, use PV wala formula. It was as simple as it is. But I was always confused. How to calculate delta U? I used to get scared when delta U was I had to calculate, or I had to calculate other terms. So it is very simple. The first law of thermodynamics, delta Q is equal to delta U plus W. It is very simple. Like one by one, we will kill all the terms in it. So delta U is done. Delta U part is already done. So there is a question for all of you. Find the internal energy of the 2 moles of the oxygen gas at temperature equal to 27 degrees Celsius. So there are 2 moles of oxygen and temperature is equal to 27 degrees Celsius. What is the internal energy of this gas? This is a diatomic gas. This diatomic gas has what energy this gas has? You have to find the internal energy of the 2 moles of the oxygen gas at temperature equal to 27 degree Celsius. Find the internal energy of the 2 moles of the oxygen gas O2 at temperature equals to 27 degree Celsius. D option. So it is very simple question. Internal energy equal to F/2 nRT. So U equal to, this is I see this oxygen O2. This is diatomic gas. Degree of freedom will be 5 divided by 2. Number of moles are given R 25 by 3 into T is 300 Kelvin. So this is 100. 12.5 kilo joule will be the answer. If they ask in calorie, then put the value of R equal to 2. In calorie, the value of R equal to is 2. So if they ask in calorie, put R equal to 2. Done? Next question. 0.064 kilogram of oxygen gas is enclosed in a vessel at a temperature of 127 degrees Celsius. The amount of heat required to double the RMS speed of its molecule. What is the amount of heat you have to supply to this gas? This is enclosed in a vessel. That means the volume is not changing. No work is involved here. So the heat you supply is directly used to change the internal energy of the gas. The heat you supplied is directly used to change the internal energy of the gas. So that amount of heat required to double the RMS speed of the molecule, you have to find. So you have to double the RMS speed of the molecules. The amount of heat supplied you have to find. Tell me the answer. The amount of heat needed. The amount of heat needed to double the RMS speed of its molecule. Can you find the answer of this question? So this temperature is 400 Kelvin. Okay, 127 degrees Celsius is 400 Kelvin. Vrms is directly proportional to root over T. Vrms is directly proportional to root over T. RMS speed is directly proportional to root over T. Now, you want to double this, double Vrms. So T will be 4 times. You will make T 4 times. You want to double the RMS speed, make T 4 times. So 4 times the change in the temperature will become 4 into 400. This is the final temperature minus 400. So 1200 Kelvin is the change in the temperature. Change in the temperature is 1200 Kelvin. Change in the temperature is 1200 Kelvin. So delta U is equal to F divided by 2 NR delta T. So F divided by 2, F is 5 divided by 2. The number of moles we have to calculate here. The number of moles is the mass, which is 64 gram divided by oxygen 32. 2 moles are there. So you multiply this with 2, the value of R. Value of R you put 25 by, so we are calculating in calorie. So 2 will be the value of R into delta T is 1200. This gets cancelled out. So 12 kilocalorie will be the answer of this question. 12 kilocalorie will be the answer of this question. Is this clear to all of you? Clear? Question number 3 is clear to all of you. So guys, there is a big announcement for all of you. NEET Endgame, the ultimate crash course, which is available at 4,999 only. But this offer is a limited offer. Use the referral code Kailash10 and enroll for this crash course at the cost of 4,999. This special price is only for a limited period and it can end anytime. I'm asking you, all of you, to just go through this course. There is a link pinned in the in this chat box. So even I am going to click on it. Like, what is the link? And it will take you to the new page. So there you get this detail of this course. There is a join this batch. Okay, 1 minute. I'm also going to click on it. So, so basically, what is the special about this batch? There are 2 physics faculties, chemistry and biology. So there is a set of 2 faculties in each subject, and all these faculties are already teaching you on this YouTube channel, Unacademy NEET English channel. You all are familiar with them. So when you are already familiar with them, you are already fan of these faculties, then why to miss the batch by them? So this is going to be the end game. This is the ultimate crash course which will help you in preparing for NEET 2024. And this price which I have written here, this is a for limited period. So don't miss this opportunity. Use this Kailash 10 referral code. This is the referral code. This is my referral code. And either you can purchase this course by clicking on the link given in the chat box or in the description. This course will be available at this price. So at 5,000 rupees price, a course with 100 days plan is available to you. What are you waiting for? Just go and enroll for this amazing crash course by the amazing set of the faculty. You don't want to miss this crash course. Already prices, we have reduced the price a lot, like that 5,000, all the 3 subjects, or by the top faculties of the Unacademy. In the 100 days you will be able to revise. So go for it. Subscribe to Unacademy. Like you can enroll for this batch. Okay, so let's move to the next topic. That is the Maxwell's speed distribution law. If you have any queries, you can ask in the comment box. KTG, how much remaining, sir? Only 2-3 slides are remaining. So Maxwell's speed distribution law. Maxwell plotted dn by dv with v. So in a container, if total n molecules are there, n molecules are there, and these molecules have random speed. It could vary from 0 to any value. So Maxwell plotted dn. What is this dn? dn is the number of molecules. dn is the number of molecules having speed from v to v plus dv, or some say v minus ka dv by 2 to v plus ka dv by 2. So it is like suppose there are molecules which have speed 1 to 100 meter per second. Okay, some might have 1.1 meter per second, 1.2 meter per second, 1.3 meter per second, 1.4 meter per second. So you are taking an interval of 0.1 meter per second. So this is dv. 0.1 meter per second is dv. So you are saying if a molecule has a speed 1 to 1.1 meter per second. So suppose there are 10 molecules with a speed 1 to 1.1 meter per second. In this range, 1 to 1.1 meter per second, there are 10 molecules. From 1.1 to 1.2 meter per second, there are 11 molecules. From 1.2 to 1.3 meter per second. So you are taking an interval of 0.1 meter per second. and in that interval the number of molecule is called dn, and that dn divided by dv. So dv we have fixed, so the number of molecule actually we are plotting. So when somebody says, okay, there are molecules with speed 1.5 to 1.6 meter per second, so we will say, okay, this speed can be treated like 1.55 meter per second. So there are 15 molecules with a speed in between 1.5 meter per second to 1.6 meter per second. Then we will say there are 15 molecules of a speed 1.55 meter per second. Okay. So he plotted number of molecules with the speed. So this speed, the maximum number of molecules have a speed, and this speed is called the most probable speed. So most probable speed is the speed which is attained by maximum number of molecule. So a speed which is attained by maximum number of molecules is called the most probable speed. So most probable speed is this speed. So this curve has maxima, and the value of v corresponding to that maxima is the most probable speed. If you increase the temperature, this most probable speed also increases. But there is a very important thing. Area of this curve is given by this formula, dn divided by dv into dv. Area of curve will be this, which is equal to integration of dn, which is equal to number of molecules, total number of molecules, ठीक है, total number of molecules. So total number of molecules does not depend on the temperature. So when you increase the temperature, this maxima will come down and this graph will spread horizontally, but the area, this area will remain same or will be equal to the area of this curve. So area A1 is equal to area A2. So area of both the curve will remain same. So the area represents the total number of molecules. So total number of molecule in both the curve will remain, in both the case will remain same. So it does not depend on the temperature. That's why area will remain same. So the area of dn by dv versus v curve will give you the total number of molecule. The area gives us total number of molecules. Total number of molecule is given by the area. Is this clear to all of you? Clear, 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 clear. So Vrms is given by this formula. So finally I am writing all the formulas. Vrms is 3 by 2. Vrms is equal to root के अंदर 3RT divided by m naught. V average is equal to root over 8 by pi RT divided by m naught. V most probable is equal to 2 RT divided by m naught. Okay, most probable is this, average is this, RMS is this. So Vrms is root 3 RT divided by m naught, V average is root 8 by pi RT divided by m naught, V most probable is root 2 RT divided by m naught. Now, which one is greater? Like the value of this will be less than 3 but greater than 2. So Vrms is maximum, then V average, and then V most probable. So this kind of question can also be asked, which one is maximum, which one is minimum, and like this comparison you can do. So Vrms, V average and V most probable are given by these three formulas. These three formulas are Very, very important. There is one more formula. Please keep this formula also in mind, and that is the V of sound. Sometimes there is a comparison between them, and that is root gamma RT divided by m naught. Gamma we will learn to calculate in thermodynamics. This is root over Cp by Cv. So value of gamma is also given as 1 plus 2 divided by f, where f is the degree of freedom. So now you can write, compare the speed of sound with Vrms, V average and the V most probable. Sometimes this kind of questions are asked. Okay, so there is a question. The relation between root mean square speed Vrms and the most probable speed Vp for the molar mass m of the oxygen gas molecule at the temperature of 300 Kelvin will be. What is the relation between Vrms and the V most probable? What is the relation between Vrms and the V most probable? What is the relation between them? Can you find the relation between these two? Relation between these two. Relation between these two. So in NEET exam, you can expect this kind of question. This is a J main question. So this question was asked in J main 2022. This is a J main PYQ. So, and this is the one of the easiest J main PYQ. That's why we can consider this in the NEET exam as well. If you remember the formula, you will be able to solve this question. So Vrms is root over 3 RT divided by m naught. V most probable root over 2 RT divided by m naught. We just divide both. So Vrms divided by V most probable comes out to be root over 3 by 2. Vrms is equal to root over 3 by 2 Vp. And this will be the answer of this question. Vrms is equal to root over 3 by 2 Vp. Question number 4 done. Clear? Question number 5. According to kinetic theory of gases, the motion of the gas molecule freezes. So there are 4 options and you have to choose the appropriate answer from the options given below. Can you answer this question? Can you answer this question? According to kinetic theory of gases, the motion of a gas molecule freezes at 0 degrees Celsius. The mean free path of the gas molecule decreases if the density of the oh no, you cannot answer this question because mean free path I haven't taught you yet. This I did not. You cannot answer. Temperature is not required here. Temperature part is not required here. So the answer of this will be B option. The next question you will be able to solve after in the end of this session. In the end of this session, we might talk about that question. I forgot about these 2 options. This part you cannot solve. Okay, let's not talk about this question. Okay. So now we are going to talk about the Dalton's law of the partial pressure. You know, ideal gas equation. PV equal to nRT. There are some other laws as well. I did not cover them. Charles law, Boyle's law. Okay. So this law is important actually. Sometimes the questions are asked on this part. Dalton's law of partial pressure says, this law states that in a mixture of the non-reacting gases, the the total pressure exerted is equal to the sum of the partial pressure of the individual gases. The total pressure exerted is equal to the sum of the partial pressure of the individual gases. So what does this Dalton's law of partial pressure says? This law states that in a mixture of the non-reacting gases, the total pressure exerted is equal to the sum of the partial pressure of the individual gases. So when there is a container, there are N1 moles of one gas, N2 moles of other gas. So total pressure is given by N1 RT divided by V, N2 RT divided by V. This is the total pressure of the gas. Total pressure of gas. So we are just adding the partial pressure of gas 1 and partial pressure of gas 2. When we are talking about the gas 1, we are not worried about the gas 2. We are simply writing the pressure of gas 1 and the pressure of gas 2 and adding them will give us the total pressure of the gas inside the total pressure of the mixture. So there is a question on that also. Question number 6 is there. A vessel of the volume 8.3 liter contain a mixture of ideal gases at 300 Kelvin. The mixture consists of 0.1 moles of N2 and 0.2 moles of O2 and 0.3 moles of CO2. Find the pressure of the mixture. Find the pressure of the mixture. So you have to find the pressure of the mixture. So this is the question. Try to solve this question. A vessel of volume, actually when I am standing in front of you now, in front of the smart board, you are not able to see the question properly. That's why I am on the other side of the smart board. It is very difficult to speak so much English. A vessel of volume 8.3 liter contain a mixture of the ideal gases at 300 Kelvin, and this mixture consists of the 0.1 mole of N2, 0.2 mole of O2, 0.3 mole of CO2. Solve this question. Can you solve this question? Okay, let's talk about it. So what we have to do is, the total pressure of this is equal to P1 plus P2 plus P3. Okay, so P equal to N1 R T divided by V, N2 R T divided by V, N3 R T divided by V. So we can write N1 plus N2 plus N3 R into T divided by V. So the total pressure of this gas is equal to N1, which is 0.1 plus 0.2 plus 0.3 into R. R is 25 divided by 3 into T. T is 300 Kelvin divided by volume. Volume is 8.3 liter. You convert this into meter cube. This 25 by 3 is almost equal to 8.3. It will cancel out and you get 0.6 into 3, 1.8 into 10 raised to the power 5. It is equal to 180 kilo Pascal, and this will be the answer. Okay, so Dalton's law of partial pressure question we have just solved. This is a question based on the Dalton's law of the partial pressure. So you just directly add the number of moles, multiply with R into T divided by molar mass, and you get the pressure of the gas. Now we will enter into the KTG part is over and the one concept is left, and that is the mean free path. So now we are going to enter into the thermodynamics part. So now till now we have we are able to understand the internal energy of the gas. The internal energy of the ideal gas is given by the F by 2 nRT. The change in the internal energy of the ideal gas can be given by F by 2 nR delta T. The change can be written by F by 2 P final V final minus P initial V initial also. C option. You were able to solve the question very late. I could not see here. Maybe this is. Okay. So let's talk about the thermodynamics. So now we are going to talk about the different processes on a gas. Change in the internal energy in that process, work done by the gas in that process, and we will learn to apply the first law of thermodynamics for any process on the gas. So this all be the study of the heat supplied to the system during a process is done under the thermodynamics. So this is the new topic, na? Like one topic we have already completed. It is feeling like a little light. I am feeling that I have already completed one topic and now we are moving to the other topic. This is a relatively easy topic as compared to the KTG, but this is lengthier than that. So let's start the topic. So thermodynamics, we will start with we are not going to start with the types of the system, indicator diagram and so on, so that you already understand. Any curve, P versus V, T versus V, P versus T, those curves are called the indicator diagrams. We draw some curves in thermodynamics, P versus V, P versus T, T versus V. These all curves are called the indicator diagram. And any curve on these plots is called a unique process, and any point on this curve is called the state of the gas. There are three types of the system which we talk about. One is the open system, where matter and the energy both can exchange with the system. You can add the matter, you can change the amount of the substance. There is a closed system. Mostly our system will be closed, where the number of moles of the gas will not change. The matter will not be added, but heat can be supplied to the system or extracted from the system. And there is one more system that is called the isolated system, where neither matter or nor exchange of the energy takes place. So three types of system are there. Mostly we will talk about the last two systems, closed system or isolated system. Okay, so this is the part I generally cover before starting the first law of the thermodynamics. So what is the first law of the thermodynamics? This law, first law of thermodynamics, is based on the energy conservation principle. The first law of thermodynamics is based on the energy conservation principle and is valid for all type of substances. This is valid for solid, liquid and gases. It is not only for the gases. Sometimes we have this mentality that after KTG we study thermodynamics, so thermodynamics is all about the gases only. No, we will mainly talk about the gases, but it is not only about the gases. So first law of thermodynamics is based on the energy conservation principle. So sometimes in NEET paper they might simply ask, first law of thermodynamics is based on which principle? It is based on the energy conservation principle, and this is valid for the all type of the substance. You can apply it on the solid, liquid or gas. According to this law, according to the first law of the thermodynamics, some part of the energy absorbed by the system is converted into mechanical work, and the remaining part changes the internal energy of the system. So when you supply the energy to the system, the some part of the energy is converted into the mechanical work, and the remaining part is absorbed by the system as an change in the internal energy. So this is the first law of the thermodynamics, and this is the statement of the first law of thermodynamics. So Is this clear to all of you? Any problem till now? Any problem here? So what is the first law of thermodynamics? According to this law, some part of the energy absorbed by the system is converted into the mechanical work, and the remaining part changes the internal energy of the system. So basically, suppose this is our system. Suppose this is our system. So you supply some energy. This is the Qn. This is energy supplied. The system has internal energy. Some internal energy was there. This system does work which is equal to W. So some part of this energy is utilized in doing the work, and some heat is ejected. This is called the Q out, and the internal energy of the system changes. Now internal energy becomes UF. This is all the energies involved are represented here. So we do the energy conservation. So we apply the energy conservation principle. Energy conservation principle says Q in the amount of heat in which is being supplied to it. It already has initial internal energy. Now its internal energy is changed to U final. Some energy is ejected out by the system, and some work is done by the system. So this is the energy conservation. So we write here Q in minus Q out is equal to U final minus U initial plus ka W. This is delta Q is equal to delta U plus W. Always keep one thing in mind, this work is done by the system. This work is done by the system. This work is done by the system. So delta Q is equal to delta U plus W, or we sometimes write Q is equal to delta U plus W. There is a problem with this delta Q path function or state function, but in physics we are not worried about the path function or the state function. We are simply saying this is the net heat given to the system, and we are representing it with delta Q. We don't care about that the state or path function. Okay. Clear. Is this clear to you? Delta Q is equal to delta U plus W. Delta U, we already know this is equal to F by 2 NR delta T. This we can directly write. Delta U we can write for any process. We need to learn work. How do we find the work done by the gas? And then we will be able to find delta Q. So now our main focus is to find the work done by the gas. Our main focus is to find the work done by the gas. Here we talk about the cylinder and piston arrangement. So work done by the gas on the piston. We will talk about that. So first law of thermodynamics clear? First law of thermodynamics clear to you? Okay. So work done by the gas on the piston. Work done by the gas on the piston. So suppose this is a cylinder and this piston is movable. There is a gas in this piston cylinder arrangement. This gas has some pressure. Let's call it P. This piston has some cross section area. Let's say A. So A is the cross section area of the piston. So gas will apply a force P into A on the piston, and this piston moves dx upward. The piston is moved by dx. This is a small displacement. So piston is moved by dx. So the work done by gas in dx displacement of piston is equal to, that work will be dw, and this is given by P into A into dx. This is the work done by the gas in a small displacement. Can I write A dx is equal to change in the volume? So this A into dx is equal to dV, or you call it change in volume. So change in volume is given by A into dx. So dw can be written like P into dV. So when you are calculating the total work, you integrate this P into dV from V initial to V final. Put pressure in terms of volume and then integrate it. And put the limits from P initial to P final. You get the work done by the gas in this process. So work done by gas is given by this formula. Work done by gas is equal to P dV from V initial to V final, and you can put P as a function of volume in this equation. Okay. Expansion work, one more thing is important about this. Area under, because this is P dV integration, area under P versus V gives us work done by gas. This is work done by gas. So this is given by area under P versus V curve. The expansion work is taken as positive. So whenever there is expansion, the volume, final volume is greater than initial volume. Suppose the process is like this. This arrow tells us it is expansion or the compression. So initial volume is this, final volume is this. So gas is pushing it outward. Work done by gas will be positive. This area is equal to work, and expansion work is positive. If this arrow is other way, then it will be compression work. So this is compression work will be negative. The work in compression will be negative and expansion work will be positive. And area under the PV curve will give you work done by the gas. Work done by the gas can be written, can be find out by the area under the P versus V curve. So there are certain processes, and let's take a small break and then we start the class again, because even I am tired. So we start the class at, it's 7:25. We start the class at 7:45. 15 minutes break we are taking. This should look classy, na? Okay. Okay. We start the class again at 7:45 p.m. Okay. No break. Oh, sir, why the work done convention for the compression and expansion are different in the physics and the chemistry? Okay, this is a good question. Basically, work done by the gas, we talk about work done by the gas on the piston. So if gas, the piston is expanding, the container is expanding, the gas is doing positive work because gas is pushing walls outward. Now they are moving outward. Only then the expansion will occur. So in that case, the work done by gas will be positive, and in the compression, work done by the gas will be negative. No, you are not asking for the break. I am asking for the break. It is not always about you. It is sometimes about your teacher as well. I got tired. I was teaching continuously for 2.5 hours. So I need a break. You don't need a break. It's a big fan of your work. Okay, thank you. So see you all after 15 minutes. Okay, take a break. You also eat something and then come to the class again with the energy to digest all the processes. I'm going to teach you all the processes like isothermal, isometric, isobaric, isothermal, adiabatic, polytropic, free expansion, cyclic. After all these processes, we will talk about the second law of thermodynamics and then entropy. So these all topic we are going to cover. So I'll be back in the 15 minutes and then we start these topic. Okay? See you soon. When will it start? On the 2nd of January. The crash course, which the link of the crash course given in the chat box will start on the 2nd of the January. So if anyone is interested in this crash course, enroll using the link given in the chat box. Guys, take a small break and then we start the class again, okay? I'll be back in 15 minutes. Guys, I'm back again. So we start the topic. It's exactly 7:45. Yes, 7:45. Okay. So we have already discussed about the work done by the gas. It is work done by the gas on the piston. Okay. So for the different process, we will learn how to calculate the work done by the gas. So first process which is done on the gas is the isocoric or isometric process. What is isocoric or isometric process? In this process, volume remain constant. In this process, volume remain constant. No change in the volume. Delta V equal to 0. Volume does not change in this process, which is the isocoric or isometric process. In isometric process, volume is constant. Okay. So work done in isocoric process, isocoric is equal to 0. There is no work done by the gas in the isocoric process. Delta Q is equal to delta U plus W. This is the first law of the thermodynamics. Here W is equal to 0. So delta Q will be equal to F by 2 NR delta T. So delta Q is also given by F by 2 NR delta T, na? You can write it like P final V final minus P initial V initial. So V is same. So P final minus P initial into volume, because volume does not change in isocoric process. So delta Q can be written like this: F divided by 2, pressure will change, F divided by 2 P final minus V P initial into V. If you write the relation between pressure and the temperature, so P equal to NR divided by V into T. So pressure will be directly proportional to temperature if volume is constant. If you plot pressure versus temperature, it will be a straight line passing through the origin. So there we can plot some curve as well. Let's call it P versus V. So for V naught and 2V naught, I am going to plot two curves. Let's say one curve is this, other is this. These both the processes are done on the constant volume. One is like this and other is like this. Let's say the pressure here is P naught and pressure here is 2P naught. Volume is V naught and this volume is 2V naught. There are two processes. This process is A, B, and this is C, D. What does this process indicate? In this process, at constant volume, you are increasing the pressure. If pressure is increasing, then temperature is also increasing. So this process AB is isocoric heating. This is called the isocoric heating. You are heating the gas without changing the volume. In this process, pressure is decreasing. So this process CD is isocoric cooling. So one is heating process and other is the cooling process. So process CD is the isocoric cooling and one is the isocoric heating. If you want to draw the PT curve or VT curve, if you want to draw PT or VT curve of these two processes, so this is a PT curve, this is a VT curve. If you want to draw these curves, so PT curve will be a straight line, because P is equal to this constant into T. Thus it will be straight line. P versus T with slope equal to NR divided by V. So it will be a straight line from origin. So PT curve will be a straight line. The PT curve will lie on these two lines. These two will lie on these two lines. So for this first process, volume is V naught. For the other process, volume is 2V naught. So the slope will be higher for this process because volume is V naught for process AB. So this AB will lie on this line and CD will lie on this line. CD will lie on this line, AB will lie on this line. We draw two more lines. B and C has pressure 2P naught. So you draw a line of 2P naught from here. You draw a line of P naught from here. So this is pressure P naught, this is 2P naught. You say A and D must lie on this line. B and C must lie on this line. So C common point is this. D common point is this. D will be this point. C will be this point. A common point is this. B common point is this. So if somebody asks you to convert a curve, yeah, P versus V plot into P versus T, you plot them like this. These are the two processes on the PT curve when they are given on the PV curve. So P versus V is converted to P versus T. Any problem here? Any problem here? Is there any problem? All clear? When we are plotting V versus T, when we are saying V versus T, so which is common between these two curves? What is common between these two curves? V is common. So you mark V naught here. You mark 2V naught here. You just draw this line. You draw this line and you say AB will lie on this line, CD will lie on this line, AB will lie on this line, CD, because for A and B volume is V naught, for C and D volume is 2V naught. So 2V naught wala line ye hai. C and D both lie on this line, A and B lie on this line. If we call the temperature of this point T naught, the temperature of this point becomes 2T naught, because here product of pressure and volume will be 2 times the product of pressure and volume at here. Here P naught V naught is equal to NR T naught. Here 2P naught into V naught is equal to NR 2T naught. Here temperature will be 4T naught. The temperature at this point will be 2T naught. So you mark 3 points: T naught, 2T naught, 4T naught. There is this line. There is this line. There is this line. So temperature of A point is T naught and A lie on this line. So A will lie on at this point. Temperature of B is 2T naught. B is here. D point and C point. C will be here. D point will be here. So the curve, this line looks like this. Matlab the curve looks like this. Are these conversion clear to you? This conversion P versus V is given. We have to draw P versus T and V versus T. Don't like this. Done? Done? तो work done in this isocoric process 0 होता है. Delta Q delta U के बराबर होता है. Delta Q and delta U are same. Delta U is F by 2 NR delta T. So delta Q is equal to also F by 2 NR delta T. In this process, you can easily find the heat given to the gas, if you know the which gas is there, what is the change in the temperature, and what is the number of moles of the gas. Class duration, this will be over by 9:30. 9:30 it will be over. So isocoric, one process is done, like one process we have completed. Let's talk about the second process, and that is called the isobaric process. In isobaric process, pressure is constant. In isobaric process, pressure is constant. So PV equal to nRT, we have ideal gas equation. So V will be equal to nR divided by P into T. So V is directly proportional to temperature. Here volume will be directly proportional to temperature. If you increase the temperature, volume will also increase. In this kind of questions, most of the time piston is free to move. Piston is free to move. If they mention this, that piston is free to move, then it will be an isobaric process. So this way you recognize this process. So isobaric process. So isobaric process is what? When piston is free to move, then that process is called the isobaric process. Okay, like let me draw a diagram here. Suppose there is a piston cylinder arrangement given to you. You are heating this arrangement. This piston is free to move. And suppose this piston is light, no mass, it does not have any mass. So pressure on outside and pressure on inside will remain same. So when you increase the temperature, according to this equation PV equal to nRT, when you increase temperature, the product of these two must increase, but the pressure is not changing because piston will adjust accordingly. This is constant. So what will happen? This piston will move upward, and that way volume of the gas will increase. So when you are heating the gas, the volume will automatically increase. So in the isobaric process, pressure is constant, temperature, when you increase the temperature, volume will increase, but the piston the piston is movable, free to move. Even if it is it has mass and it is free to move, again the process will be isobaric. So piston is free to move. So work done in isobaric process, is equal to integration of P dV. Pressure is constant, so we take out it from the integration. dV is V initial to V final. So we write P delta V as the work done by the gas in isobaric process. This work done is PV final minus PV initial. Pressure is same. So you can also write it nRT final minus nRT initial. So work done in isobaric process has one more formula which you remember, but this formula most of the time we ignore, and that formula is nR delta T. So nR delta T is the work done in the isobaric process. So work done in the isobaric process is equal to nR delta T. This is a very important formula, very useful. So whenever temperature change is given to you, number of moles you know, you can directly write the work done in the isobaric process, and that is equal to nR delta T. So nR delta T is the work done by gas in the isobaric process. The work done by the gas in the isobaric process, clear? Is this clear to all of you? Work done by gas in the isobaric process. Work done by gas in the isobaric process, clear to everyone? Clear, all clear? Let's talk about the conversion. Like again, if P versus V curve is given to us, how do we convert into P versus T and V versus T? So this is So these processes are, suppose this is P versus V curve is given, and both the processes are given like this. At constant pressure, volume is increased, constant pressure. So this is V initial, V final, P naught, 2 P naught. This is V naught, this is 2 V naught. Okay. So one process is given like this, one other is given like this. So this is process AB, this is process CD. So what is happening here? At constant pressure, gas is expanding. So AB is isobaric expansion. Volume is increasing in this process. And CD is isobaric compression. Isobaric expansion and the isobaric compression. So when you plot T versus V, yeah, or you say V versus T. So V versus T, P versus T. How do we plot V versus T and P versus T? So in this case, when we are plotting P versus V versus T, which thing is common here? Volume. You mark V naught and 2 V naught here. Okay. Now V versus T curve will be, V will be equal to NR divided by P into T. It will be straight line through origin. So we draw two lines from origin of different slope. We draw one line this, one line this. So we are saying that A and D have volume V naught. So A and D have volume V naught. C and B have volume 2 V naught. So C and B have volume 2 V naught. So C and B should lie on this, A and B on this. AB has more pressure, and pressure is in denominator. This is the slope of V versus T. Which has more pressure, it will have less slope. AB will lie on this, CD will lie on this. So C lie on this, and this C will be this point, D will be this point, A will be this point, and B will be this point. So the AB will look like this, and CD will look like this, AB, and this is CD. Conversion clear? Is this conversion clear to you? How do I convert this process into this one? Let's say suppose it is a cyclic process, and we have this line as well, like this. So we will be able to do this question also, because isocoric we have already studied at the constant volume, and isobaric we are studying. So isobaric, these two processes are isobaric and these two are isocoric. So now what will happen? We will add these two lines as well, and these two lines. So this curve look like this. This graph will look like this on the VT curve. So VT curve will look like this. Clear? Done. So VT curve is given, PV curve is given. Now we are going to talk about the PT curve, P versus T. So in P versus T, what is common? Pressure. Pressure is common in both the curve. What I'll do is, I'll mark P naught and 2P naught. I'll draw these two lines first. This is P naught, this is 2P naught. So A and B lie on this, AB lie on this, C and D lie on this, C and D will lie on P naught one line. Okay. Now, what about these 2 points? So if I said the temperature of this point is T naught, then the temperature of this point will be 2T naught. Temperature of this point will be 4 T naught. Temperature of this point will be 2 T naught again, because this volume is 2 V naught and pressure is P naught. So P naught into 2 V naught is equal to nRT. P naught V naught is, we are calling nRT naught. Again mark here three temperature, T naught, 2 T naught and 4 T naught. So this is 4 T naught, this is 2 T naught, this is T naught. So temperature of C and A. So C and A, C will be this point, A will be this point. The temperature of D is this, D will be this point, and the temperature of this is 4 T naught. That point is B point, B will lie here. Now you join these points. A look like this. B to C. Yes, B to C look like this. C to D. Did I make some mistake here? Will they pass through? Origin? P versus T will pass through origin or not? Yes, they will pass through, because BC process is this, isocoric. So isocoric process should pass through the origin. PV curve of isocoric process will pass through the origin like this. We could have drawn this like this also. So A to B, C to D. This will be the process on PT curve. So PT curve will look like this. VT curve will look like this. Are these curves clear to you? Are these curves clear to you? So on the previous page, what we have done, work done is equal to NR delta T. Okay, work done in the isobaric process we already know, that is equal to NR delta T. Work done is equal to NR delta T. So in isobaric, work done is equal to NR delta T, and we know delta U is equal to F by 2 NR delta T. So delta Q here will be F by 2 NR delta T plus NR delta T. This is the heat supplied or extracted in isobaric process. Work done is NR delta T. Delta U is always F by 2 NR delta T. You add both, you get the delta Q in the isobaric process. So this was all about the isobaric process. Pressure constant, work is NR delta T or P delta V. These are the conversion of the P versus V curve into the V versus T or P versus T curve. Clear? So there is a question on this isobaric process. I want all of you to try this question. Let's see how many of you are able to solve this. A diatomic gas does 200 joule of work when it is expanded isobarically. The heat given to the gas in the process in joule is, what is the amount of heat given to the gas if the work done in a isobaric expansion is equal to 200 joule. So what amount of work will be done by the gas? The heat given to the gas will be, we have to calculate. So heat given to the gas, what is the amount of heat given to the gas? If this gas does 200 joule of the work when it is expanded isobarically. When this gas is expanded isobarically, what is the amount of heat given to the gas in this process. Can you solve this? No? Yes? So see, work done in isobaric process is given by nR delta T. Okay, and this is given 200 joule. 200 joule is equal to nR delta T. Delta U is given by F by 2 nR delta T. And this gas is diatomic. Degree of freedom will be 5 divided by 2. nR delta T is 200 joule. So this comes out to be 500 joule. Delta Q is equal to delta U plus ka W, and it comes out to be 700 joule. It comes out to be 700 joule. Done. So this is the question number 7, where we have to find the heat supplied in the isobaric process. Heat supplied in the isobaric process will be given by this formula. Let's talk about the molar heat capacity. There is a term that is called the molar heat capacity of the process. So every process has its own molar heat capacity. So what is the definition of the molar heat capacity? Heat given per mole of a gas in a process to change its temperature by unity is called the molar heat capacity of the process. So amount of heat given to a gas per mole of a gas to change the temperature by unity is called the molar heat capacity. So molar heat capacity of any process is equal to delta Q divided by N delta T, or you say we can write delta Q is equal to N into C of process into delta T. So from here we get C of process is equal to delta Q N divided by N delta T. So when number of moles is 1, change in the temperature is 1 unit, then molar heat capacity of the process is equal to delta Q. So when you take number of moles equal to 1 and changes the temperature of the 1 mole of the gas by 1 unity, the amount of heat supplied delta Q will be equal to C of that process. So what you have to do here, you have to just divide delta Q by N delta T and you get the molar heat capacity of that process. So molar heat capacity of any process is given by delta Q divided by N delta T. So C of any process, this is the final formula, which is equal to delta Q divided by N delta T. With the help of this formula, you can find the molar heat capacity of any process. Molar heat capacity of any process can be found out with the help of this formula. So there is a relation between Cp and Cv. What are Cp and Cv? Molar heat capacity at constant volume. Molar heat capacity in a process. Molar heat capacity at constant volume is defined like Cv. Molar heat capacity at constant volume is defined like Cv. So Cv is given by delta Q divided by N delta T. So what is the delta Q in isocoric process? It was equal to F by 2 nR delta T, and you divide it by N delta T. So Cv is given by F by 2 R. So CV of this process is equal to F by 2 R. So molar heat capacity at the constant volume is equal to F by 2 R. So if you know the gas, you can directly write the CV of that gas. If it is monoatomic gas, then CV is 3 by 2 R. Diatomic gas, CV is equal to 5 by 2 R. Molar heat capacity at constant pressure. Molar heat capacity at constant pressure is called CP. What was the amount of heat in the isobaric process? That was F by 2 nR delta T plus nR delta T. We just derived this formula. And if you divide this delta Q by N delta T and this by N delta T, you get CP. So CP is given by F by 2R plus R. This F by 2R is CV. So CP minus ka CV is given by R. So CP minus CV is equal to R. CP minus CV will be equal to R. This is a very important relation. Oh wow, this line is so perfect. So the relation between CP and CV is CP minus CV is equal to R, and this is a very important relation for ideal gas. Okay? So this is for ideal gas. For ideal gas, CP minus ka CV is equal to R. CP minus CV equal to R. Can I write for any process, not only about isocoric, for any process, can I write delta U is equal to NCB delta T? Can I write it always like this? Can I write delta U for all the process, for any process, any NCB delta T? Then you might get confused, sir. CV is only for constant volume wala process. No. CV is equal to F by 2R and delta U is equal to N into F by 2R delta T. So I am just replacing F by 2R. So for any process, delta U is equal to NCV delta T. Delta U is equal to NCV delta T. For any process, delta U will always be equal to NCV delta T. This you can always write. So now you can write dq for any process. You can write dq is equal to NCV dt plus PdV. For any small step, you can always write like this. This step you can always write. This is the work in a small step. NCV dt is the small change in the internal energy, and dq is the heat given in a small step. Got it? The relation between CP and CV and this all clear to you? All of this is clear to you. So there is a question coming to you on this part only. You have to solve this question. So a monoatomic gas perform work of Q by 4 when Q is the heat supplied to it. Find the molar heat capacity. Find the molar heat capacity of the gas during this transformation. A monoatomic gas perform a work of Q by 4 where Q is the heat supplied to it. Find the molar heat capacity of the gas during this transformation. Can you solve this? Molar heat capacity of the gas you have to find during this transformation. Can somebody find the answer of this question? No, sir, we cannot find the answer of this question. This is very difficult question, and we are not supposed to solve questions like this. If this is the case, then please let me know. No sir, this kind of questions are not to solve. Only questions which can be solved are to solve. B and D. Okay, so some of the students have already answered this question. So what will be the answer of this question? So let's solve it. You know, what was the definition of molar heat capacity of any process? So C of any process is given by delta Q divided by N delta T. This is the formula of the process, C of the process. Here, can I find the delta U? It will be equal to Q minus ka Q by 4, and that is equal to 3Q by 4. Delta U, heat supplied is Q, work is Q by 4. So the difference of both will give me delta U, and delta U is F by 2 NR delta T, and this is equal to 3Q by 4. Okay. Okay. What is the degree of freedom? This is a monatomic gas, so it will be 3 by 2 NR delta T is equal to 3Q divided by 4. 3 and 3 gets cancelled out. This also gets cancelled out. So from here, can I write Q divided by N delta T? Q divided by N delta T will be equal to 2R. And that is the molar heat capacity of the process. So for this process, molar heat capacity is given by this formula. C for this process is equal to 2R. Done. Indirectly, we have to solve this question. This was a very good question. Question number 8, a really amazing problem. Monoatomic gas perform a work of Q by 4. Q is the heat supplied. We first calculated delta U. We found the N delta T from there. We put the N delta T in that case, and we get the answer. Let's talk about the isothermal process. So when a gas is expanded or compressed in a container, this container is conducting cylinder. If cylinder is conducting, then heat exchange will be there between the surrounding and the gas. So the temperature of the gas will be equal to temperature of the surrounding if process is slow. Process is slow. So by applying external force, you can expand the gas. Expansion will be there. By applying external force downward, there will be compression. So compression and expansion will be done by the external force. There is the exchange of heat between the surrounding and the gas. So temperature of the gas remain constant, and if this process is slow, then temperature remain constant, and this process is called the isothermal process. In isothermal process, temperature of gas remain constant. Temperature of the gas remain constant in isothermal process. So PV is equal to constant. PV equal to constant. This is the equation of the isothermal process. In isothermal process, delta U will be equal to 0 because delta T is equal to 0. So delta U will be equal to 0 because delta T is already 0. Now, work done in isothermal process is equal to PdV integration from V initial to V final. This PV can be written like PV equal to nRT naught. from here I replace this P as nR T naught divided by V into dV from V initial to V final. So work done is equal to nR T naught ln V final divided by V initial. This is the work done, or you could write it P initial V initial ln V final divided by V initial, or equal to P final V final ln V final divided by V initial. These are all the formulas to find the work done in a isothermal process. So in isothermal process, work done can be found out with the help of these formulas: P initial V initial ln V final divided by V initial, or P final V final ln. So this is also one formula, nR T naught divided by ln V final divided by V initial. Work done by the gas in isothermal process. In isothermal process, delta U is equal to 0, work is equal to nR T naught ln V final divided by V initial. So delta Q is equal to W is equal to nR T naught ln V final divided by V initial. This is the value of delta Q. Value of delta Q is this. Value of W is this. This way we find the work in the isothermal process. The PV curve for the isothermal process is given like this, PV curve. If this is at T1 temperature, this is at T2 temperature, then this temperature will be greater than T1. So expansion work, and this is expansion, this is compression process. At higher temperature we are compressing, at the lower temperature we are expanding. This kind of graph we will get if PV is equal to constant. It will be a rectangular hyperbola. X into y equal to constant is a rectangular hyperbola. Yes, temperature is constant. See, you have to watch the complete lecture, only then it will be beneficial. Otherwise, this the time you have given to this lecture will not be of any use. So watch it till the end. This is important actually. And I have also increased the speed so that we are able to finish this lecture by 9:30 anyhow. So 9:30, after 9:30 you will be free from this class. Okay. So let's talk about the fourth process, that is called the adiabatic process. A process on a system is said to be adiabatic if no heat is supplied or extracted from the system during the process. There is no heat exchange between the surrounding and the system even for a step. So delta Q is equal to 0 for the adiabatic process. For adiabatic process, delta Q is equal to 0. So delta work is equal to minus delta U. There is this relation between the work and the delta U for the adiabatic process. So a process on a system is said to be adiabatic if no heat is supplied or extracted from the system during the process. Delta Q is 0, work is equal to minus ka delta U. There is a relationship between pressure and volume for the reversible adiabatic process. The reversible adiabatic process means at every step this condition is being followed. What is the condition? That no heat is being supplied to the gas or extracted from the gas for even a step of the process. For a small step of the process, this condition is holding. Then that process is called the reversible adiabatic process. In adiabatic process, delta Q is equal to 0. So we have to find that relation between the P and V. So what we do here is, we know dq is 0. So dw for a small step is equal to minus ka du. Okay, dw is equal to minus ka du. dw is given by pdv is equal to minus ka ncv dt. We can write it like this. We have to find the relation between pressure and volume. So we have to eliminate this term T. We know PV equal to nRT. This is ideal gas equation. We differentiate this equation. So we get VdP plus ka PdV is equal to nR dt. This is, we have differentiated this equation. From here we can write n dt equal to, so PdV is equal to minus ka n dt can be written like, so Cv divided by R Vdp plus Pdv. Now all the terms are in terms of P and V only. So Pdv term we take on one side, Pdv we take on the that side. So we get Pdv 1 plus Cv divided by R, and on the other side minus Cv divided by R Vdp. If we take the LCM Pdv, this becomes R plus Cv divided by R is equal to minus Cv divided by R Vdp. This thing is Cp. R and R gets cancelled out. This is Cp. So Cp divided by Cv into Pdv is equal to minus ka Vdp. This is called gamma. Now we integrate it. Gamma dV divided by V is equal to, or take minus on this side, dP divided by P. Integrate it. When you integrate it, you get minus gamma ln V final divided by V initial is equal to ln P final divided by P initial. We take this inside, so ln V initial divided by V final to the power gamma is equal to ln P final divided by P initial. This is a relationship between pressure and the volume. You see, here it was V final divided by V initial, but when we take minus inside, then we have to do reverse of this, like V initial will be upward and V final will be downward. From here we get P initial V initial to the power gamma is equal to P final V final to the power gamma. So we say P V to the power gamma is equal to constant. P V to the power gamma is equal to constant for reversible adiabatic process. So for reversible adiabatic process, PV to the power gamma is equal to constant. This is the relation between pressure and the volume. PV to the power gamma is equal to constant. Reversible adiabatic process. So all the processes which are sudden processes, sudden with the or in an insulated container, those processes are called the adiabatic process, because in those processes gas does not get time to interact with the surrounding or to heat. It is not able to exchange the heat with the surrounding, and those processes are called the adiabatic process. So for any adiabatic process, if it is a sudden process or with an insulated container, it is the adiabatic process. Adiabatic process we have done. So what is the work done in the adiabatic process? So we know there is a relation between P and V. PV to the power gamma is equal to constant. Let's call this constant equal to C. So work is defined like work is equal to integration P dV from V initial to V final. This is the work. From here I can write P equal to constant divided by V की power gamma. Constant divided by V की power gamma. So work is equal to this constant divided by V की power gamma into dV. This can be written like constant into V to the power minus gamma into dV. So work is given by constant V to the power minus gamma plus 1 divided by minus gamma plus 1. We have simply used the formula of integration. So work is given by this constant into V final to the power 1 minus gamma minus V initial to the power 1 minus gamma divided by 1 minus gamma. This is the work done by the gas in adiabatic process. See, P initial, V initial to the power gamma is constant and P final, V final to the power gamma is also equal to constant. So now we put these formulas here. So we get work is equal to, we put this formula here. So P final, V final to the power gamma into V final to the power 1 minus gamma minus P initial, V initial to the power gamma, V initial to the power 1 minus gamma divided by 1 minus gamma. So work done is equal to P final, V final minus P initial, V initial divided by 1 minus gamma. This is the work done in the adiabatic process. So adiabatic work is equal to nR delta T divided by 1 minus gamma. So work done in the adiabatic process is equal to nR delta T divided by 1 minus ka gamma. This is the work done in the adiabatic process. nR delta T. Remember this formula, nR delta T divided by 1 minus gamma. So if delta T is positive, then work will be negative because gamma is greater than 1. What is this gamma? This gamma is, I told you na, gamma is Cp divided by Cv. Ratio of the molar heat capacity at the constant pressure and molar heat capacity at the constant volume. The ratio of both is called the gamma. And gamma is always greater than 1. Gamma is always greater than 1. So if delta T is positive, means internal energy is increasing. If delta U is increasing, delta T is positive, matlab delta U is increasing, work will be negative. So work will be negative if delta U is positive. If delta U is negative, then work will be positive. So yes, value of gamma also you can write like in terms of degree of freedom also you can write. Let me write here it here. So gamma is also given by Cp by Cv. So Cp is F by 2 plus 1 R or Cv is F by 2 R. So gamma is given by 1 plus 2 divided by F. It is greater than 1. Gamma is greater than 1 and it can be expressed in the terms of degree of freedom like this. Gamma clear? So this part is clear to all of you. Adiabatic process, work done, adiabatic process equation, everything about the adiabatic process I have just covered. Now let us talk about the adiabatic and isothermal process P versus V graph. So basically this is also very interesting topic. When we talk about the P versus V plot for the adiabatic and the isothermal process, so one is adiabatic and one other is the isothermal curve. Out of these two, one is adiabatic and one other is the isothermal. So can you identify which one is adiabatic and which one is the isothermal? And how do you decide that? So to decide that, this point will help you. This point is going to help you. What does this point say? At this point, The pressure and the volume for both the processes is same. Pressure and the volume for both the process is same at this point. So for isothermal process, P equal to V is equal to constant. So if I want to find the slope, so V dP by dV plus ka P is equal to 0. We just differentiated this equation with respect to volume. So dP divided by dV, I get minus ka P divided by V. This is the slope of isothermal PV curve. Isothermal P versus V. Slope of adiabatic. So adiabatic curve is PV to the power gamma is equal to constant. When you differentiate it with respect to volume, you get gamma V to the power gamma minus 1 into P plus V to the power gamma dP divided by dV. This is equal to 0. Now, you take V to the power gamma minus 1 common. This is gamma into P plus. This is V into dP divided by dV. And this is equal to 0. So dP divided by dV from here, we get minus ka gamma P divided by V. The magnitude of the slope of adiabatic curve, this is the slope of adiabatic. So at this point, you have pressure and volume same for both. So this P by V will be same for isothermal and the adiabatic. But gamma is greater than 1. So the magnitude of the slope of adiabatic curve will be more. It is negative, but the magnitude will be more. Magnitude of slope of adiabatic curve will be more. So which has more slope? If a curve is like this, it has 0 slope. If a curve is like this has some slope, but it is negative. This has more slope. Magnitude of the slope is higher, but it has negative slope. So which one have more slope? Or more negative slope? This. So this will be adiabatic and this will be isothermal. So when we are talking about the expansion, adiabatic curve will be below isothermal. When we are talking about the compression, if you are compressing, compression, then adiabatic will be above the isothermal. Isothermal and adiabatic curve will look like this in expansion and the compression. Adiabatic and isothermal process, P versus V graph for compression and expansion. Both the curves are given here. Both the curves are given here, adiabatic and isothermal. Can you compare them? There is one more process. Basically, it is a collection of so many processes. And these processes are called the polytropic process. For a polytropic process, PV to the power m is equal to constant. This is the equation. We generally don't take m equal to 1. Otherwise, it will be isothermal equation. We don't take m equal to 1. In this polytropic process, delta U is always equal to NCV delta T. I told you delta U can be written like this for any process. Work will be equal to NR delta T divided by 1 minus M. I am not going to again derive this. We have just derived for the adiabatic PV ki power gamma equal to constant. It was NR delta T divided by 1 minus ka gamma. Or P final V final minus P initial V initial divided by 1 minus M. Generally this form is used. Okay. Always remember M is not equal to 1. M should not be equal to 1. Otherwise work will be infinite. Now, delta Q is equal to delta U plus W. Delta Q can be written like NC of process into delta T. We just defined this formula. This is NCV delta T plus NR delta T divided by 1 minus M. So for polytropic process, C process is given by CV plus R divided by 1 minus M. This is a very important formula. Tomorrow at 2 p.m. we are going to practice the question in the special class. The link of the special class is given in the description. So you have to attend that class as well for the practice. So for a polytropic process, for any polytropic process, for any polytropic process, for any polytropic process, C of that process is equal to CV plus ka R divided by 1 minus ka M. Process is written like PV ki power M is equal to constant. This is very important, extremely important formula. The C process wala jo formula hai na, this formula is extremely important formula. You remember this derivation or not, but this formula is important. This formula is very important. So polytropic process we have just completed, and there is a question for all of you. A monoatomic gas undergoes a process which is P equal to C divided by T, where C is constant. Find the molar heat capacity of the process. Find the molar heat capacity of the process. Guys, I have already taught units and dimension on this channel. Basic maths, which is the trigonometry part, and a separate lecture on the vector and the calculus. If you complete all these lectures which are covered by me, this is really going to help you in understanding the physics. Physics is difficult because we don't understand the basic mathematics part that I have covered in great detail. Now we are covering a topic which is again a very important topic. I'll cover one more topic, that is the thermal expansion, heat transfer, and the calorimetry. That also we will cover on this channel. This way I am going to teach you most of the 11th topic on this channel. Done, bacha? Done. Are you able to find the answer? The answer is, most of the students are saying, sir, the answer will be C option. Is that a correct answer? C option is the correct answer or not correct answer? I have already shared the basic maths PDF in the Telegram channel of this, the common Telegram channel of this platform, and in my Telegram channel as well, KS Physics. In that also I have shared the PDF. KS Physics, Kailash Sharma ka initials KS Physics. That on that channel and that group I have shared the PDF. These topics are independent topic. Thermal physics is the independent topic. That's why I first started teaching this topic, because this is independent. So here they are saying monoatomic gas is given, and you have to find the molar heat capacity. So C for the process is given by CV plus ka R divided by 1 minus M. CV, it is monoatomic gas. CV equal to F by 2R plus R divided by 1 minus M. This is the C process. But there is a problem. We are not given P as a function. PV equal to M equation is not given here. What is given here? PT equal to constant. This is given. Now we can write T equal to PV divided by NR and put it here. it becomes P square V equal to constant. If you take root, then it will become P V to the power 1 by 2 equal to new constant. So value of M is equal to 1 by 2. C of process is equal to 3 by 2 R divided by 1 minus 1 by 2. It becomes 7 by 2R is the answer. 7 by 2R will be the answer of this question. 7 by 2R will be the answer of this question. Clear? Clear ba? Is this question clear ba? Question clear ba? Not clear ba? Clear ba or not clear ba? A, yes, A option is the answer. No, did I say C option? No, A option is the correct option. There is a very special case, like so many questions can be answered by analysis of this. Expansion of the gas from same initial state to the same final volume. A gas is there, you are performing different process on that gas, you are expanding it from same initial state to same final volume. We draw the PV curve and we do the analysis here. What is that analysis? Let's say gas is at this point. This is the initial volume, this is the final volume. Okay? This is P initial. So it has P initial, V initial and T initial. These are the pressure, volume and the temperature. If you expand this gas isobarically, isobaric expansion will look like this. See, we have PV to the power M is equal to constant. So when you say M is equal to 0, when you put it here, V to the power 0, it becomes 1. It implies P equal to constant. So when M is equal to 0, we get isobaric process. So you say for this process M is equal to 0 and it is isobaric. Got it? This is isobaric process. We draw the isothermal. For isothermal M is equal to 1. Isothermal. Because if you write M equal to 1, this equation becomes like PV equal to constant. And that is isothermal process. This is isothermal expansion. Adiabatic curve will be below. M becomes gamma and this is adiabatic. And if any, suppose you say PV to the power 2, that will be below this. So value of M, we are increasing, the curve is going like this. M0, M1, M gamma and M infinity. If M is infinity, that will be Isocoric process. At constant volume, pressure will fall. So these are few processes. Suppose value of M is 1 by 2, yes. So value of M is 1 by 2, then process will look like this. If value of M is greater than gamma, the process will look like this. Okay? Clear? This thing is clear to all of you? So you can draw all the processes. So many processes on this curve. If they all start from the same initial state, but the final volume is same. Now we have to do some analysis here. What are those analysis? First one is, when it is isothermal process, here delta T is equal to 0, means T initial is equal to T final. So temperature at this point and temperature at this point are same. Temperature, same. When we talk about this point, M, when M is less than 1, Here, see, the temperature of this point will be greater than temperature of this point. Why? Because product of P into V, volume is same, but pressure at this point is greater than pressure at this point. Temperature, because you know PV equal to nRT. If this is same and this is increasing, then temperature will increase. So at this point, pressure is lower than this point. All the points above this will have higher pressure than this. And volume for all the points is same. N and R are same. That means their temperature will be more than this. And for the points below it, the pressure will be less. Temperature will be less than this. For all these points, temperature will be less than temperature of this point. So I can say one thing certainly, that at this point delta T will be greater than 0, delta T will be greater than 0. Why? Because temperature at this point is equal to temperature at this point. And these all points have temperature greater than this temperature. Means all these points have temperature greater than this. So final temperature is greater than this. So if I say PV to the power 1 by 2, PV ki power 1 by 2, the gas is expanded according to this equation. What will be the effect on the temperature? So if you are expanding a gas and value of m is less than 1, expanding a gas and value of m is less than 1, the temperature will rise. So in that case, temperature will rise. And for these, delta T will be less than 0. So here I can write, for in case of expansion, in case of expansion, in case of expansion, if m is less than 1, delta T will be greater than 0. And if m is greater than 1, delta T will be less than 0. Got it? Is this clear? And then let us talk about other. For the adiabatic process, delta Q is equal to 0, adiabatic process. Here the work done and delta U cancel out each other. Work done and delta U. Work done is area under this curve, PV curve is the work done, and delta U both cancel out each other. At this point, delta U is 0, isothermal process, delta U 0, temperature is not changing, but there is a positive work. So delta Q will be positive here. Same for this point, delta Q will be positive and delta Q will be positive. So all the points above, all the processes above adiabatic will have delta Q positive. Downward will have delta Q negative. Downward processes have delta Q negative. So in case of expansion, if m is less than gamma, delta Q is positive, m is greater than gamma, delta Q is negative. And even you can compare the work as well. In which process will be the more work, that also can be compared with this curve. We can compare heat we can compare, so many things we can compare from here. So I am going to give you a question, and with that question, I'll cover one more concept. So there is a question: a monoatomic gas is expanded according to the process P T ki power m. No, not T ki power m. This is PV की power m is equal to constant. So if we are expanding a gas according to the equation process PV की power m equal to constant, find the value of m for which the molar heat capacity of the process is negative. Find the value of condition of m, condition on m for which molar heat capacity is negative. Can you answer this question? Can you answer this question? In which case molar heat capacity will be negative? Molar heat capacity will be negative. In which of these cases molar heat capacity will be negative? Molar heat capacity will be negative out of in which case out of these. Please don't forget to like the session. Tomorrow at 2 p.m. we have a special class. In that special class we are going to do practice. There is a crash course starting on 2nd of January on Unacademy. The link of that crash course is given in the chat and the description. There is a referral code as well which you can use. That is the Kailash 10. Kailash 10 is my referral code. That course is available at 4,999 for a very short duration. It might change any time. Before it changes, do enroll for this crash course. In this crash course, all your faculties which you study on this channel, from them you study on this channel, are going to teach you. Okay, so have you solved it? So you all are saying, sir, m must be less than gamma. See, you missed one point. That point is very important. What is the molar heat capacity of the process? What is the formula? That is delta Q divided by N delta T. So when you say this is negative, that means delta Q and delta T should have opposite sign. Do you agree or not? If delta Q is positive, then this should be negative. If this is positive, then this should be negative. You agree? If somebody says that C of process should be negative, that means delta Q divided by N delta T should be negative. So one out of these should be positive and other should be negative. Clear? So can you tell me in which reason this condition will hold? So this is the reason, this one. Here delta Q is greater positive and delta T is negative in this region. Here they both are positive, here they both are negative. In this region, isothermal, below isothermal delta T is negative, above adiabatic delta Q is positive. In this region they both are of opposite sign. So for the value of m less than gamma greater than 1, they both have opposite sign. So delta T here is, here delta T is negative and delta Q is positive. So C of process is negative. Done. C of process is negative. So this is a very good question actually. Do you like this question? And please guys, I want all of you to comment after this class. Once this class is over, please comment whatever you feel about this class. You like it or not? What changes can be done? That looks good actually. It means you are interacting with me. It feels like that. So I want all of you to comment on this class after the class, when class is over. Okay, please do that. Don't forget about it. Do it today, do it tomorrow, do it 3 days back, 4 days, 5 days, 6 days after, but you have to do it. And even that you can do with my other lectures. If you like them, please write that. I can work for you, like I can take a 4 to 5 hours long session, then at least you can do a comment on my classes in return of the hard work I am doing for you. Okay, thank you. So there is one more process, students, that is called the free expansion. This is a very special process. Like, you have to consider certain things that this is happening, and according to that we are answering. So this container is insulated container. No heat exchange is there between gas and surrounding. So no heat exchange is there between gas and surrounding. And this is vacuum. Pressure here is 0. And this is gas. Gas is filled in this part. Okay. This piston is released. This is a special process, okay? And this is called the free expansion. This is called the free expansion of the gas. So there is nothing to resist. There is nothing to resist the piston va. There is nothing to resist the piston. That means कि work done by gas is equal to 0. Delta Q is already equal to 0 because there is no heat exchange. So delta U is also equal to 0. Delta U is Fy to Nr delta T. So change in temperature is also equal to 0. This is called isothermal expansion. Hence, product of P and V is constant. So if the volume gets doubled, the pressure will be half. Only this is the case. This you have to remember. Okay. Can you remember this? PV equal to constant. PV equal to constant. There is nothing to resist the piston. So work done by gas is equal to 0. Delta Q is equal to 0. Delta U is equal to 0. Delta U is 0. That's why delta T will be 0. Okay, got it. Free expansion done. This was free expansion. Let's talk about the cyclic process. I did not see cyclic process in your syllabus, but it was mentioned that different processes. So different processes, so cyclic process is also a process. So that's why we have to cover the different processes. Okay, so cyclic process also I have to cover. When the final state of the gas, is same as initial state in a process, then such process is called the cyclic process. When final state of the gas is same as the initial state, then such process is called the cyclic process. So there are, suppose there is a cyclic process like this. This is the cyclic process, PV. So from here, it started like this and it came back. Okay, this is the cyclic process. Let's call this point A and this point B. So it is a combination of two processes. This is expansion this is compression. So in expansion, the work done is this area, and expansion work is positive. The compression, the work done is this area. Work done in the cycle is equal to area of the loop. Area of loop. Loop will be there, no? Area of the loop is the work done. When this is anti-clockwise, an anti-clockwise cycle is there, work is negative. Work is negative. When anti-clockwise cycle is there, work is negative. Because there, in that case, more compression work will be there. When there is a clockwise cycle, like this, now more expansion work is there, less compression work is there. So work done by gas in clockwise cycle is positive. So in this case, work will be positive. Again, the work will be equal to area of that loop. And in there is one more cyclic process, but it is of no use. Then you'll say, sir, why are you teaching that? Let's say this is the process. No work is obtained hence no use of this cyclic process. So there is no use of this cyclic process if we are not getting any work. If we do not have loop area, then there is no use of this kind of cyclic process. So when final state of the gas is same as initial state in the process, then such process is called the cyclic process. Finally, it might be the combination of the multiple processes. The final state and the initial state must be same for a process to be cyclic process. Done. So there is a question. This part we have already covered. This part we have already covered. You just have to find the efficiency of this process. So this is a process. Let's call it ABCD. So this ABCD is a process where initial volume is V0. It isocorically heated, then isobarically expanded, isocoric cooling, isobaric compression. You have to find the efficiency of this cyclic process. The other part we have already completed, na? P versus T and V versus T in the isobaric process. You want to try this? I am waiting for all of you to try this question. Okay, let's talk about this P versus T and the V versus T. So this is P versus T, this is the V versus T. What we do is, this is A, B, C and D, given like this. So in these two curves, pressure is common thing. So we mark P0 here to P0 here. We draw two lines with pressure P naught and pressure 2P naught. A and D lie on this line, B and C lie on this line. Okay, A and D and B and C lie on this line. This process AB, and these are at constant volume. At constant volume, P equal to NR divided by V into T. V is constant. So relation between P and T is linear. So P and T curve will be straight line passing through the origin. The one with the more volume will have less slope. You draw two straight line from origin. The one with the more volume will have less slope. So more volume are 2B naught. So C and D lie on this. A and B lie on this. So this will be B point. This will be A point. This will be D point. This will be C point. Now just join these points. A to B, B to C, C to D. This is the conversion. If you miss this part, I have already covered this in the isobaric process. But even if you miss this part, then you can learn it from here. So this is the conversion, and this kind of question can be easily asked. Like this is given and 4 options are given like this. In NEET also they can ask. Let us talk about volume V versus T. So V is common here. So just mark two volumes with V naught to V naught. Draw two lines. Same method you can use. Draw two lines. Okay. So with volume V naught, A and B lie on this line, and 2V naught, C and D lie on this line. Okay. Now we are drawing P versus T. So take these two processes, this one and this one. They are at constant pressure. So V equal to NR divided by P T. So it is a straight line passing through the origin with two different slopes. So the one with the higher pressure will have the less slope. So these two, B and C, will have less slope. So B and C lie on this, then A and D lie on this. So A here, D here, B here, and C here. The final curve will look like this. This will be the graph of this V versus T curve of P versus V. All these things are clear to you. Now let us talk about the efficiency. Did I define the efficiency? So efficiency of a cyclic process. Work output divided by Qn, or you call heat given to system. Heat given, not heat ejected. It is the heat given to the system. Is called the efficiency. Like this ratio is called the efficiency. Work output divided by Qn, which is the heat given to the system, is the efficiency. So in some part heat will be given or some part heat will be ejected out. So you have to just divide this work by the heat given to the system. So let's talk about the efficiency part. This part is not mainly for NEET, but matlab a process, they might ask a part of this. They will not ask this complete question. They might ask a part of this, in which part of this process the heat is absorbed or in which part heat is emitted. This kind of question can be asked on this part, okay? So this process is A, B, C, D, A, B, C and D, like this. So name of the process here, delta U here, W here, delta Q here. Net AB process, BC process, CD process and DA process. There are 4 processes. We just make this table. That we start from here. We went here, went here, went here, went here. We came back to the point A. So net delta U will be 0 because initial and final state are same. So in cyclic process, delta U, value of delta U is equal to 0. Net delta U is 0 in the cyclic process. So here delta U will be equal to 0. Area of the loop will be equal to work. So what will be this area? This is V naught, this is P naught. So area will be equal to P naught V naught, and the sum of these two is equal to delta Q, which is also P naught V naught. Okay, this line is over. This process is isocoric and this one is also isocoric. So AB and CD will have 0 work. AB and CD will have 0 work. The work done in the process dA in this process will be area under this curve, that is V naught into P naught, minus ka V naught into P naught. So AD, this is minus ka P naught into V naught. Sum of all these 4 should be equal to this. So this will be 2 P naught V naught. This will be 2 P naught V naught. Then only the sum will be equal to. And you could directly write the area of under this curve will be this. This height is 2 P naught. This volume is V naught. This area will be 2 P naught V naught. Okay. Now let us talk about process AB. So in this process, this is isocoric heating. So delta U is equal to we have to define here, this is a monoatomic gas. Otherwise, we will not be able to solve the question. So in process AB, this is isocoric, F by 2 NR delta T, or delta U can be written like F by 2 P final V final minus P initial V initial. Okay. So P final V final 2 P naught V naught minus P naught V naught. So it becomes P naught V naught. So delta U becomes, if this is monoatomic gas, this becomes 3 by 2 P naught V naught. The sum of these two will be equal to 3 by 2 P naught V naught. This heat is positive, this heat is given to the system. We are talking about B to C. Again, 3 by 2 P final V final, which is 4 P naught V naught. P initial V initial, 2 P naught V naught. It will be 2 P naught V naught. This comes out to be 3 P naught V naught. And this is 5 P naught V naught. This is also positive. C to D, final pressure, final volume is 2 P naught V naught, and that is 4 P naught V naught. This comes out to be minus ka 3 P naught V naught. This is minus 3 P naught V naught. In this D to A, final pressure P naught V naught minus 2 P naught V naught. This is minus P naught V naught. So this is minus ka 3 by 2 P naught V naught. So this comes out to be minus ka 5 by 2 P naught V naught. This heat is given to the system and this heat is given to the system. So Qn is equal to this plus this, 13 P naught V naught divided by 2. Efficiency comes out to be work is P naught V naught divided by 13 divided by 2 P naught V naught into 100. It becomes 200 divided by 13%. And this will be the answer. 200 divided by 13% will be the answer. So this is your question number. Oh, question number 3 is written there. I don't know where. Question number 11. So you can find the delta U, W, delta Q, everything you can find with the help of this table. So so whenever there is a question of cyclic process, always try to solve that question using this table. Use this table to solve the question. Done. Okay. Now we are towards the end of this session. Like only few things are remaining. 15 to 20 minutes it will take. Then we will be done with this topic and this course. Carnot cycle. This is the special type of cycle. An ideal reversible closed thermodynamic cycle with successive operation involved as isothermal expansion at T1 temperature, adiabatic expansion, isothermal compression at T2 temperature, and adiabatic compression is called the Carnot cycle. So Carnot cycle is a special kind of cycle where we are doing certain processes, and this is an ideal reversible closed thermodynamic system, which is called the Carnot engine, Carnot cycle. And in this Carnot cycle, what happens? There are these processes. AB is isothermal expansion. So heat enter to the system at this point. B2C is adiabatic expansion. No heat is added to the system at this point. C to D, isothermal compression. Heat eject out of this. Let's call it Q2. And D2A is adiabatic compression. The most important thing about this is this Q1 upon Q2 is equal to T1 upon T2 only for the Carnot cycle. Only for the Carnot cycle, Q1 upon Q2 is equal to T1 upon T2. Q1 upon Q2 is equal to T1 upon T2. This relation holds only for the Carnot cycle. So for the Carnot cycle, these are the processes involved in this. So at constant temperature, this cycle takes heat that is equal to Q1. This temperature is higher temperature and it is equal to T1. And at constant temperature, it eject heat which is Q2, and at temperature T2, it eject heat. So the relation between Q1 and in these two processes only it is taking heat and ejecting. So Q1 upon Q2 is equal to T1 upon T2. This relation holds only for the Carnot cycle. So this is a just reversible cycle which has these four operations involved: isothermal expansion, adiabatic expansion, isothermal compression, and adiabatic compression is called the Carnot cycle. So let's talk about the second law of thermodynamics. So there is not a special statement about the second law of the thermodynamics. It is a collection of many statements. Those talk about the natural processes, whether this process will occur or not. So there are multiple statements which combinedly or collectively gives us the second law of the thermodynamics. So out of these statements which are important in the physics are Kelvin-Planck statement and Rudolf-Clausius statement. These two statements you have to keep in mind. You have to be prepared that they might be asked in the exam. Kelvin-Planck statement says it is not possible to design a heat engine which work in a cyclic process and whose only result is to take heat from a body at single temperature and convert it completely into the mechanical work. तो इन्होंने कहा according to Kelvin-Planck statement, you cannot design an engine which uses a cyclic process and it only takes heat and does not reject heat. The total heat intake is converted into the mechanical work. So this kind of engine cannot be designed. This was the statement by the Kelvin-Planck. This is the Kelvin-Planck statement. There is another statement, Rudolf-Clausius statement. It is impossible to make a heat flow from a body at lower temperature to a body at the higher temperature without doing external work on the working substance. So the second statement is like you cannot, it is not possible to heat flow from lower temperature to higher temperature. Obviously heat automatically flow from higher temperature to lower temperature. It cannot flow from lower temperature to higher temperature without doing any external work. So these are obvious statements. So let us talk about heat engine. So heat engine is a device that converts thermal energy into mechanical work. It's called a heat engine. So heat engine takes energy at temperature T1. Let's call it the heat taken by heat engine is Q1. It rejects some heat at temperature T2 and some work you get, this mechanical work you get. So obviously there will be this relation Q1 minus Q2 will be equal to W. Efficiency of this engine is equal to work divided by heat input, which is Q1. You can write work is equal to Q1 minus Q2 divided by Q1. It comes out to be 1 minus ka Q2 divided by Q1. If Carnot engine is this, if this is Carnot engine using Carnot cycle, then we know that Q2 divided by Q1 is equal to T2 divided by T1. So efficiency becomes 1 minus T2 divided by T1. So if you know the temperatures, then you can find the efficiency of the Carnot engine. This efficiency neta can never be 1 because to do so T2 must be equal to 0 Kelvin minus 273 degrees Celsius. This is called the sink. This is called reservoir. So from the reservoir, hot reservoir, it is taking heat and it is ejecting heat at in the sink at T2 temperature. So efficiency of this engine can never be equal to 1 because for doing this, the sink must be kept at 0 Kelvin. If you put value of T2 0, then efficiency will be 1 or like 100% efficiency you will get. So even Carnot engine cannot have 100% efficiency, but Carnot engine will have maximum efficiency. No other engine working between these two temperatures will have efficiency more than Carnot engine. So Carnot engine efficiency will be maximum. Okay. So there is a question on the Carnot engine. I have just taught you. I don't think it is part of your syllabus, but just being on the safe side, I am teaching this because I told you it won't take more than 10 to 15 minutes. So this question also we are going to solve. A Carnot engine whose heat sink at 27 degrees Celsius has an efficiency of 25%. By how many degrees should the temperature of the source be changed to increase the efficiency by 100% of the original efficiency? So we want to increase the efficiency by 100%. So initially efficiency is 1 by 4. We want to increase it 100%. We want to double it. We want to make it 1 by 2. So what should be the temperature of the source should be changed? Okay. This is the temperature of the sink, which is T2, which is equal to 300 Kelvin. We have to find temperature of T1. Initially efficiency is equal to 1 by 4. 25% matlab 1 by 4. This is equal to 1 minus T2 divided by T1. Can we find T2 divided by T1? This comes out to be 3 by 4. So T1 will be equal to 4 into 300 divided by 3. It will be 400 Kelvin. So T1 will be 400 Kelvin. Now we want to increase the efficiency by 100%. Matlab we want to make it double. Matlab 1 by 2. So 1 minus T2, which is 300, divided by new temperature. Let's call it T dash. So T dash will be equal to 600 Kelvin. So T dash minus old temperature T1 is equal to 200. So we need to increase the temperature by 200 degrees Celsius. So B option will be the correct option. It was just a simple question of the efficiency. Efficiency be equal to 1 minus ka T2 by T1 formula we have to just apply. Question number 12 is done. Carnot engine. There is a concept of heat pump or refrigerator. That phrase we use in our home. That concept of that. Heat pump or refrigerator. A device used to pump out heat from system at lower temperature to one at the higher temperature is called the heat pump. But this process is not done by its own. So this is T2, lower temperature. You are taking out heat from here, which is Q2. This is heat pump. You are ejecting that heat at higher temperature, that is T1. You need to do some work, otherwise this process will not be possible. So Q2 plus W is equal to Q1. There is a coefficient of performance defined. Coefficient of performance. Coefficient of performance is desired effect divided by work. So we are taking out heat. So this is our desired effect. It is also called COP. COP will be Q2 divided by W will be Q1 minus Q2. This comes out to be 1 divided by Q1 divided by Q2 minus ka 1. If Carnot cycle is used, COP becomes 1 minus T1 divided by T2 minus ka 1. COP can be greater than 1 as well, but efficiency cannot be greater than 1. But COP can be greater than 1. Coefficient of performance can be greater than 1. That's why, there is a question on refrigerator. Like sometimes they say, if we open the door of the refrigerator, the room will not cool down. Cooling, it won't do cooling to the room. The problem is, you are opening the door. The refrigerator is taking heat from here. The electricity is adding the energy that is being ejected out on the backside of the refrigerator in that room only. So heat ejected by refrigerator is Q1, taken by refrigerator is Q2. W is added into Q2 and then it is rejected in the same room. So ultimately this is the heat which is additionally being ejected in the room. That external work or the electric energy we are supplying, that is additional energy that is coming to the room. That's why room will not cool down, it will heat up. You cannot do the cooling by refrigerator. If the backside part of the refrigerator is outward, it is ejecting heat outside, then it can be done. The same thing is done by the ACs. The AC eject heat outside. There is an external unit. There is an internal unit. Okay, heat pump and refrigerator is done. Entropy. There is a concept of the entropy. Entropy is the measure of the disorder of molecular motion of the system. Entropy is written like ds is equal to dq divided by T. This is the formula of the entropy. ds is equal to dq divided by T. S we use to represent the entropy. ds is entropy change. You can write dq is equal to T ds. If you integrate it, heat given is equal to area under T versus S curve. T versus S curve will give you the area under T versus S curve will give you the heat given to the process. When substance is changing its phase, this part is mainly covered in chemistry properly. So we are not giving that much time in this class. When there is a phase change, then temperature remain constant during the phase change. So delta S is equal to delta Q divided by T. So delta S is equal to M into L divided by T. L is the latent heat. I hope you all have studied this in calorimetry. Latent heat. So delta S becomes equal to M into L divided by dt. When temperature is changing of the substance, so ds is equal to dq here becomes ms dt divided by T. You integrate it, you get delta S is equal to M into S dash ln T final divided by T initial. This is the change in the entropy when you are heating or cooling a substance that you do in the calorimetry. We do this part in the calorimetry, this one. To raise the temperature of a substance by dt, we supply the amount of heat equal to ms dt. Ms dt by T, we integrate it, we get the change in the entropy. Processes on the ideal gas. So ds is equal to dq divided by T. And dq can be written like ncv dt plus pdv, and we are dividing it by T. This is a small step. So delta S becomes ncb ln T final divided by T initial. Here we write T final divided by T initial plus. How do we solve this? So P divided by T can be written like nR divided by V, ideal gas equation. Put it here. nR will be out and this will become ln V final divided by V initial. This is entropy change for any process on ideal gas. So if the process is isocoric, V final and V initial become same. Delta S is equal to NCV ln T final divided by T initial. Isobaric process, delta S. In isobaric process, what will happen? This can be written like pressure is constant. So this will be T final divided by T initial. So this becomes NCP ln T final divided by T initial. You'll take it common. CP plus R will be CP. Similarly, you can do for the other processes. Other process can also be entropy can be calculated. Entropy part is, I think, is not that important, or you have already studied it in chemistry, that based on that you can solve the question. So the last concept, that is the mean free path of the gas molecules. This is important. This is way too important actually, the mean free path. The path traveled by the molecules, this is the part of the KTG, kinetic theory of gas. I am covering this in the end. The path traveled by the molecules between the two collisions is called the free path, and the mean of this distance traveled by the molecule is called the mean free path. So on an average, distance traveled by the molecule between two collisions is called the mean free path. Okay, mean free path. So how do we decide the mean free path? Let's say there is this molecule. It is moving and we are considering all the molecule at the rest. This molecule is moving with V average. Okay, with V average this molecule is moving. So any molecule having its center in this cylindrical region, any molecule having its center in this cylindrical region, so any molecule having its center in this cylindrical region will collide with this molecule. Center, let's say there is this molecule, almost identical. Okay, let's say there is this molecule and there is this molecule. So the center of this is on this boundary line and the center of this is here, center of this is outside. What is going to happen is it will just touch this molecule because this distance is, see, what is this distance? So the diameter of this molecule is d and radius of this cylindrical region is also d, or you call it d equal to 2r. This is also equal to d equal to 2r. So this radius is r, this radius is r. They will touch each other because the distance between their center will be 2r exactly. But this center is inside. The distance, this distance is less than 2r. D dash is less than 2r. So this will collide with this molecule. This distance is greater than 2r. D double dash, this is greater than 2r. This will not collide. Every molecule whose center lies in the cylindrical region will collide with this molecule. Do you understand this part? Any molecule whose center lies in this cylindrical region of radius 2r will collide with this molecule. So there are few terms, like one is N, number of molecules per unit volume. So N is equal to capital N divided by volume. Okay, N is equal to capital N divided by volume. Number of molecules in delta L length will be equal to N pi into 2r ka square into delta L. These many molecules will be in this delta L length of this cylinder. This is the volume of the cylinder, and you multiply with the number of molecule per unit volume. So number of molecule in delta L length of the cylinder will be this. So number of molecule is this, N pi 2r ka square into delta L. Delta L is distance traveled by delta T time. So in delta T time, this molecule is covering a distance of delta L. So delta L is equal to V average into delta T. So delta L is equal to V average into delta T. So when it is traveling this distance delta L, number of molecule it is colliding is this. So on an average, free distance, which is the mean free path, lambda mp, will be distance traveled divided by number of collision. So V average into delta T divided by N pi into diameter ka square into V average into delta T. This comes out to be 1 upon N pi into D square. This is the mean free path. But there is a problem. We have considered all the molecules at rest. So mean free path when all other molecules are considered at rest is 1 upon pi d square into n. When we consider the motion of all the molecules, the lambda mean free path becomes 1 upon root 2 pi d square into n. This is the mean free path of molecules. So lambda mean free path is equal to 1 upon root 2 pi d square into n is the capital N divided by volume. It depends on the volume. It will depend on the volume. To increase the volume, lambda mean free path will increase for the same number of the molecules. So some says it does not depend on the temperature. If volume is constant and you are increasing the temperature, it will not change. Lambda mean free path will not change. So if we increase temperature by keeping fixed volume, lambda mp will not change. It will not depend on the temperature if volume is constant. Volume is constant, then it will not depend on the temperature. This is the mean free path of the gas molecules. Guys, KTG and thermodynamics part is over. There is one more time we are going to talk about this NEET endgame crash course which is the ultimate crash course for all of you, specially designed by your favorite educators. These all educators will be teaching in this crash course for NEET 2024. This batch is starting on 2nd of the January, and if you please don't miss this opportunity, because in this 100 days course they all are going to revise all the concept of the physics, chemistry and biology in only 100 days in this crash course. There is a referral code also, Kailash 10. Use this referral code and enroll for this NEET Endgame crash course. There is a link which is pinned in the chat box. You can directly click on that. After this class, just go through this crash course. Just check once what we are offering in this crash course. Everything you will get, the details of this crash course you will get through that link only. So link is given in the chat. Please go through it. This crash course is available at 4,999 rupees, and this is a limited period offer. You don't want to miss it. So maybe anytime it can change. So go and enroll using the link given in the chat box or description. If anywhere it is required, then apply. There's a Kailash 10 referral code. You'll get the additional discount. Lakshya MBBS batch is there for NEET UG 2024. There are 250 live classes with the tip and trick to crack the exam. 5-month crash course is there. 10 mock tests are there. You can also enroll for this batch with the same referral code. And the link of this course is also given in the description. Early Enthus 2.0 batch for NEET UG 2025. There is this batch is for 2025. You can start your preparation at the early stage at rupees 32,062 rupees. There is the Unacademy scholarship test for NEET UG and get a 90% scholarship. There are 60 questions, which 60-minute online test is there. Syllabus is physics, chemistry, biology. 4 marks for each correct answer and -1 for each incorrect answer. You must enroll for this Unacademy scholarship test, and the link of this scholarship test is also given in the description. Tomorrow at 2 p.m. we are going to practice the questions of the thermal, KTG and thermodynamics, which I have covered today. Question practice will be done in this special class, which is tomorrow at 2 p.m. The link of the special class is also given in the description. Aspire, achieve and the advance to your medical glory. You can practice the last 10-year PYQs free of cost on Unacademy platform. You can enroll for this also by scanning this. Okay, so guys, I have completed KTG and thermodynamics. 4 topics I have completed till now. One is units and dimension, error and measurement, vernier calipers and the screw gauge. All those topics are covered in the first lecture. In second lecture I covered the function and the trigonometric function. Third lecture I have covered the vectors and the calculus part of the basic mathematics. This was my 4th lecture where I have covered the KTG and thermodynamics. In the next lecture I'll try to cover the other one. I'll take an important topic which should be independent from the mechanics, and that way we are going to carry forward these sessions. And sir, your daughter's name? Olive. So as I have already asked you to comment your experience about this class in the chat once this class is over. Not in the chat, in the comment box. In the comments you must share your thoughts, like which topics you need, which topics of class 11th you want me to cover on priority. You can mention them. I'll schedule classes according to that only. Thank you. Thank you so much for being in the class till 10 p.m. Like for the last 5 hours we were together. We have completed a very important topic. Thank you everyone, and see you all tomorrow at 2 p.m. in the special class. Don't miss this special class, otherwise there is no use of this theory cover. This theory is complete when you practice the questions. So tomorrow at 2 p.m. special class link in description. just check description and enroll for that special class right now, so that you will get the notification. Now, right now you enroll for that special class. Okay, thank you bacho, thank you, take care, good night, and don't forget to comment. Okay, bye.